to picture a world dominated by enormous beasts, both towering and airborne, casting vast shadows over a landscape teeming with new life and verdant greenery. Dinosaurs, with some as heavy as 10 elephants, thrived and transformed their habitats throughout the ages. This saga unfolds over the Triassic, Jurassic, and Cretaceous periods, marking a pivotal era in Earth's saga. The story of dinosaurs begins during the Triassic period, which spanned from around 253 million years ago to approximately 249 million years ago. This period followed a mass extinction, the most significant in Earth's history, clearing the way for new life forms. The planet was in a state of recovery, and it was characterized by a warm climate with high levels of carbon dioxide and relatively dry conditions leading to vast deserts. During the Triassic, the continents were not yet the separate landmasses we know today. Instead, they existed as a single supercontinent known as Pangaea. This massive land formation influenced global weather patterns and allowed for various ecosystems to evolve. Since most of the land was situated close to the equator, it experienced a generally warm climate, making it conducive to the development of diverse life forms. The flora of the Triassic period was largely dominated by gymnosperms, such as cycads and conifers, providing a different backdrop from the dense forests that eventually characterized later periods. However, as new species emerged with the rise of dinosaurs, even the plant life began to evolve in response to these newly dominant herbivores. It marked the beginning of a fascinating and intricate relationship between dinosaurs and their ecosystems. By the end of this period, the stage was set for what would come next. The Triassic led into the Jurassic period, during which dinosaurs truly became the dominant terrestrial vertebrates. From relatively small creatures in the Triassic, they would evolve into various forms and sizes, paving the way for the rich biodiversity that would thrive for millions of years. The story of the earliest dinosaurs takes us back to the Triassic period, over 250 million years ago. At that time, the Earth was a vastly different place, dominated by reptiles and the aftermath of a mass extinction that had wiped out many species. Within this context, a group of small, agile dinosaurs began to emerge, arising from the archosaur lineage, which also includes modern birds and crocodiles. These early dinosaurs were probably no larger than a dog, roaming the lush, warm environments that dotted the ancient landscapes. One of the main distinguishing features of these early dinosaurs was their unique stance and posture. Unlike the sprawling limbs of many reptiles, early dinosaurs developed a more erect posture with legs positioned directly beneath their bodies. This adaptation allowed for more efficient movement and greater agility. In addition, they possessed a number of skeletal features that set them apart, such as hollow bones that reduced weight and a specialized hip structure that supported bipedalism, or walking on two legs in many species. The diet of these early dinosaurs varied, which further contributed to their evolutionary success. Some were carnivorous, with sharp teeth and claws designed for predation, while others evolved to be herbivores, sporting flat teeth suitable for grinding plant material. This adaptability to different diets allowed them to thrive in various ecological niches. Their growth patterns were also noteworthy. Many grew rapidly in their early years, which is thought to have provided them a better chance of survival against predators. As the Triassic period progressed, these early dinosaurs began to diversify and evolve into the more familiar forms we recognize today. They laid the groundwork for the incredible variety of dinosaur species that would dominate the Earth for the next 150 million years. Understanding the origins of these magnificent creatures invites us to marvel at the incredible journey of life on our planet, a story shaped by adaptation, survival, and evolutionary innovation. The rise of dinosaurs as the dominant terrestrial vertebrates is a fascinating tale woven into the fabric of Earth's history. During the late Triassic period, over 200 million years ago, the planet was undergoing significant transitions. At this time, dinosaurs emerged amidst a backdrop of environmental changes, such as shifting climates and the breakup of continents. These new creatures were uniquely adapted to thrive in diverse habitats, setting the stage for their ascendancy. One explanation for their dominance lies in their remarkable adaptations. Dinosaurs exhibited a variety of physical characteristics that allowed them to exploit various ecological niches. For instance, some developed strong limbs that provided the ability to run swiftly, while others grew long necks to reach foliage high in trees. This adaptability enabled them to occupy terrestrial habitats ranging from dense forests to open plains, outcompeting other reptiles of the time. Furthermore, their reproductive strategies contributed to their success, as dinosaurs laid numerous eggs, allowing for a greater chance of survival in a world full of predators. Another theory revolves around the role of climate in their dominance. During the Mesozoic era, the climate was generally warmer and wetter than today, providing lush environments conducive to the growth of vegetation. This abundance of plant life supported massive herbivorous dinosaurs, which in turn became sustenance for the carnivorous species. The stability and richness of their ecosystems likely played a pivotal role, giving dinosaurs the resources needed to flourish over millions of years. Lastly, competition and extinction events shaped the evolutionary landscape. As dinosaurs proliferated, they faced challenges from other reptiles and mammals. Understanding that their success benefited from both adaptive traits and the gradual extinction of competing species provides a clearer picture of their dominance. Each factor interweaved with the others created a robust framework for dinosaurs to thrive, ultimately leading to their reign as the rulers of the Earth for more than 160 million years. The combination of adaptability, favorable climates, and ecological shifts paints a vivid picture of a world where these magnificent creatures were king. When dinosaurs first emerged during the Triassic period, around 240 million years ago, the Earth was a vastly different place. At that time, much of the land was consolidated into a single supercontinent known as Pangaea. This colossal landmass created a variety of environments, ranging from arid deserts to lush coastal regions. The surrounding oceans were teeming with life, and the atmosphere was rich in carbon dioxide, contributing to warmer global temperatures. The ecosystems present during that era were predominantly dominated by reptiles and amphibians. The flora included ferns, cycads, and ginkgos, which flourished in the warm and humid conditions. These plants were crucial as they formed the foundation of the food web, providing nourishment for herbivorous dinosaurs. Their ability to adapt and evolve was greatly shaped by the availability of these plants, which influenced feeding strategies and ecological roles among the early dinosaurs. As dinosaurs began to diversify, the ecosystems also underwent changes. The gradual breakup of Pangaea led to the formation of distinct habitats, allowing different dinosaur species to evolve according to their environments. For example, some dinosaurs evolved to thrive in forested areas, while others adapted to life in open plains. This varying landscape played a significant role in the evolutionary paths of these creatures, fostering specialization and competition within their ranks. The interplay between dinosaurs and their ecosystems was complex and dynamic. As new plant species emerged and the climate fluctuated, dinosaurs continued to adapt in real time. This relationship, shaped by the intricate balance of food webs and environmental conditions, not only influenced the survival of dinosaurs, but also paved the way for their dominance in the Mesozoic era. Their evolutionary journey was a testament to the resilience and adaptability of life on Earth, set against the backdrop of a continuously shifting planet. The Triassic period, which spanned from approximately 253 million to 249 million years ago, marked a significant turning point in Earth's history. This era followed the Great Permian Extinction, the most devastating extinction event in our planet's history. As the climate began to stabilize, it created an array of environments that set the stage for the rise of the dinosaurs. During the Triassic, the climate was generally warm and dry, characterized by long seasons with limited rainfall. This environment led to the formation of vast deserts and seasonal habitats, which profoundly influenced the types of vegetation available. As plants adapted to these dry conditions, they began to evolve into new forms that could withstand aridity, paving the way for more diverse ecosystems. These adaptations were crucial for the herbivorous dinosaurs that emerged during this time, as they relied on vegetation for survival. Additionally, as the continents were beginning to drift apart from the supercontinent Pangaea, geographical diversification played a critical role. Dinosaurs were able to colonize various niches and adapt to different environments. This separation allowed for the emergence of distinct dinosaur species, each uniquely adapted to its surroundings. Such diversity not only increased their chances of survival, but also laid the groundwork for the evolutionary success of dinosaurs, which would dominate the planet in the following Jurassic period. Thus, the combination of climatic conditions, evolving flora, and changing geography fostered an environment where early dinosaurs could flourish and diversify. They were able to adapt to their surroundings, leading to varied forms and sizes that would continue to evolve for millions of years. The Triassic period didn't just witness the birth of dinosaurs, it set them on a course to become one of the most successful groups of animals in Earth's history. The Triassic period, which spanned from about 253 million to 248 million years ago, marked a pivotal time in Earth's history, particularly for the evolution of dinosaurs. At this time, the planet was recovering from the Permian-Triassic extinction, the most significant extinction event in Earth's history. This period saw the rise of the first true dinosaurs alongside other fascinating creatures. Among the major dinosaur species of the Triassic, the most notable include the theropods and the early prosauropods. Theropods, known for their bipedal stance and often carnivorous diets, were characterized by their sharp teeth and clawed hands. One of the earliest known theropods is Eoraptor, which stood on two legs and was relatively small. It represents an evolutionary link between the earlier archosaurs and the larger, more recognizable dinosaurs that would come in later epochs. On the plant-eating side, prosauropods like Plateosaurus emerged during the late Triassic. These dinosaurs were larger, quadrupedal creatures that exhibited characteristics leading towards the more massive sauropods we often envision today, like long necks and long tails. With forelimbs that were slightly shorter than their hind legs, these gentle giants were primarily herbivorous, grazing on the lush vegetation that started to fill the recovering landscape. As the Triassic unfolded, it can be seen as the cradle of dinosaur evolution, where the groundwork was laid for the diverse forms that would dominate the Mesozoic era. The adaptations these creatures developed during the Triassic not only positioned them for survival, but also set the stage for some of the most iconic dinosaurs that would flourish in the periods that followed. These early glimpses into their lives show us the remarkable journey of evolution, shaped by environmental changes and the ancient Earth's ecosystems. The end of the Triassic period, roughly 200 million years ago, marked a pivotal moment in Earth's history known as the Triassic extinction event. This event was one of the 5 major mass extinctions where an estimated 75% of all species on the planet vanished. The extinction was precipitated by a combination of climate change, volcanic eruptions, and possibly a meteor impact, leading to severe environmental upheavals. The loss of biodiversity during this time created a significant opportunity for the surviving species to adapt and evolve. Among the fortunate survivors were the early archosaurs, a group that would eventually include dinosaurs. With the drastic reduction in competition and predation, these archosaurs began to diversify and fill the ecological gaps left behind by the extinct species. They evolved into a variety of forms, leading to various adaptations that would allow them to thrive in the changing environments. Importantly, the warmer climates and abundant vegetation of the Jurassic period created ideal conditions for these creatures to flourish. The evolutionary advantages displayed by dinosaurs, such as their upright posture and efficient locomotion, contributed to their rapid ascent during the Jurassic period. Unlike many of their contemporaries, dinosaurs were not only able to compete effectively for food, but also adapted to numerous niches, whether flying high in the skies or reigning over the land. These adaptive traits enabled them to become the dominant terrestrial vertebrates for over 100 million years. Ultimately, the end of the Triassic extinction event served as a catalyst for the rise of the dinosaurs. Ultimately, the end of the Triassic extinction event served as a catalyst for the rise of the dinosaurs. Their ability to exploit the newly available resources and adapt to dynamic environmental changes set the stage for an extraordinary era of life on Earth. This fascinating transition underscores how extinction, though devastating, can also usher in new beginnings, giving rise to some of the most iconic creatures in our planet's history. The Jurassic period, spanning from approximately 153 million to 148 million years ago, represents a fascinating chapter in Earth's history. This era followed the Triassic period and set the stage for dramatic shifts in both dinosaur species and ecosystems. During the Jurassic, we witness a robust diversification of dinosaurs, leading to the emergence of well-known groups such as the enormous sauropods, which include the Brachiosaurus and Diplodocus. These gentle giants roamed in herds, using their long necks to reach high into the treetops for foliage. In addition to the thriving sauropods, the Jurassic was crucial for the rise of theropods, including the fearsome Allosaurus and the iconic early birds like Archaeopteryx. The evolution of these species reflects a dynamic ecosystem where competition and predation shaped survival. The mix of large herbivores and agile predators drove the biological clock forward, leading to advancements in physical traits such as the development of flight and enhanced hunting tactics, which would characterize future animal lineages. The flora of the Jurassic period also underwent significant changes. The planet witnessed the dominance of ferns, cycads, and conifers, which established lush forests across vast continents. These ancient plants provided not only food for herbivorous dinosaurs, but also created diverse habitats filled with insects and other animals. The spread of these plants facilitated more complex food webs, where different species began to interact in increasingly intricate ways. Furthermore, the Jurassic was marked by geological changes that shaped the environment. The breakup of the supercontinent Pangaea began during this period, leading to the formation of distinct landmasses. This continental drift fostered evolutionary pathways that created unique ecosystems. As environments shifted due to climate changes, dinosaurs adapted in remarkable ways, leading to the diverse array of species that we study today. This period of innovation and transformation laid the groundwork for the flourishing of life that would continue into the Cretaceous and far beyond. During the Jurassic period, which spanned from about 200 to 150 million years ago, the Earth's continents were in a state of dramatic transformation. This era was marked by the breaking apart of the supercontinent Pangaea, leading to the gradual drift of landmasses. This continental drift significantly influenced the evolution and distribution of dinosaurs, as it altered their habitats and the climates they inhabited. As the continents began to separate, vast oceanic expanses formed between them, creating isolated environments for dinosaur populations. This isolation allowed different species to evolve in unique ways, leading to distinctive adaptations suited to their specific habitats. For instance, as North America drifted away from Europe and Africa, dinosaurs in these regions began to diverge from one another to adapt to their new surroundings. This process laid the groundwork for the incredible variety of dinosaur species we recognize today. Additionally, the shifting continents affected global weather patterns and climate conditions. During the Jurassic, the Earth experienced warm, humid climates that were conducive to lush vegetation. This rich plant life not only provided ample food resources for herbivorous dinosaurs, but also influenced the types of carnivorous species that emerged to prey on them. Dinosaurs had to adapt to changing ecosystems, which further propelled evolutionary changes in their physical characteristics and behaviors. Overall, the effects of continental drift during the Jurassic period played a pivotal role in shaping the course of dinosaur evolution. The isolation fostered by drifting landmasses encouraged divergent evolution, while the changing climates influenced survival and development. This fascinating interplay between geological processes and biological evolution underscores the complexity of life on Earth during one of its most dynamic periods. During the Jurassic period, which spanned from roughly 201 to 145 million years ago, the landscape was vibrant and lush, filled with a diverse array of plant life. This era saw the rise of ferns, cycads, and the first flowering plants, all of which played a crucial role in shaping the diets and lifestyles of the dinosaurs that roamed the Earth. The abundance and variety of flora not only provided food, but also influenced the evolutionary pathways of these magnificent creatures. Herbivorous dinosaurs, such as the long-necked sauropods, thrived on this rich vegetation. These giants evolved immense bodies and long necks, allowing them to access tall trees and abundant ground cover. They consumed vast amounts of foliage to support their massive bulk. This reliance on flora not only dictated their feeding behavior, but also their social structures. Traveling in groups likely helped them locate food sources and evade predators. Meanwhile, carnivorous dinosaurs also benefited from this floral diversity indirectly. The presence of numerous herbivores created a stable food chain. Predators like the fierce Allosaurus capitalized on the abundance of prey. Their evolution was shaped by the availability of herbivores, as these prey species adapted to the changing landscape and flora, creating a delicate balance within the ecosystem. The lush Jurassic flora not only nourished dinosaurs, but also contributed to the overall climate of the planet. The extensive growth of plants played a role in reducing carbon dioxide levels and influencing temperatures, creating an environment conducive to both plant and animal life. This complex interplay between flora and the prehistoric giants of the Jurassic illustrates how essential vegetation was to the survival and evolution of dinosaurs during this remarkable period in Earth's history. During the Cretaceous period, which spanned from around 146 million to 66 million years ago, dinosaurs showcased a remarkable array of adaptations that allowed them to thrive in diverse environments. This dynamic era saw the emergence of various species, each uniquely suited to their habitats. Some dinosaurs developed physical features that enhanced their survival, such as specialized teeth and beaks for different diets. For instance, herbivorous dinosaurs like Triceratops developed wide, flat teeth that aided in grinding tough plant materials, while predatory dinosaurs like Velociraptor had sharp, serrated teeth, perfect for tearing flesh. Locomotion was another critical area of adaptation. Dinosaurs evolved various body shapes and sizes, influencing their movement and behaviors. Some, like the swift-running iguanodon, were built for speed, which helped them escape predators, while heavier, more powerful dinosaurs, like T-Rex, had strong limbs suited for short bursts of speed to catch prey. Some, like the swift-running iguanodon, were built for speed, which helped them escape predators, while heavier, more powerful dinosaurs, like T-Rex, had strong limbs suited for short bursts of speed to catch prey. Additionally, several species developed impressive armor or protective features, such as the bony plates and spikes seen in Stegosaurus, providing them with defense against attacks. The Cretaceous climate also played a significant role in shaping dinosaur adaptations. As sea levels fluctuated and vast forests spread, dinosaurs adapted to exploit these changing environments. For example, the wide distribution of flowering plants during this period promoted the evolution of various herbivores, enabling dinosaurs to diversify their diets and habitats. Some species became semi-aquatic, like the hadrosaurs, which developed webbed toes for better swimming capabilities. Lastly, social behavior and reproductive strategies evolved during this period. Many dinosaurs began to exhibit complex social structures, moving in herds for protection and foraging efficiency. Evidence suggests that some, like the duck-billed dinosaurs, may have engaged in nesting behaviors, providing care for their young and ensuring the survival of the next generation. This blend of physical adaptations, behavioral strategies, and environmental interactions illustrates how dinosaurs thrived during the Cretaceous, leaving behind a legacy that continues to captivate our imaginations today. During the Cretaceous period, which lasted from approximately 145 to 66 million years ago, a remarkable transformation occurred in the plant kingdom with the diversification of flowering plants, also known as angiosperms. This shift was not just a floral evolution. It had profound effects on the entire ecosystem, including the evolution of dinosaurs. As flowering plants began to dominate landscapes, they brought new food sources and habitats that could greatly benefit certain dinosaur species. Angiosperms evolved various adaptations that made them incredibly successful. Their flowers attracted specific pollinators, which created new relationships and dependencies among species. As these plants became more widespread, they provided dinosaurs with a richer variety of food options. Herbivorous dinosaurs, in particular, thrived on the leaves, fruits, and seeds of flowering plants, allowing those species to proliferate and adapt over generations. This increase in food resources likely influenced the size, shape, and behavior of these herbivorous dinosaurs, leading them to develop new feeding strategies. Moreover, the landscape itself began to change. With flowering plants came new types of ecosystems, such as flowering shrublands and forests, which offered diverse habitats for dinosaurs. This development allowed for a wider array of ecological niches. Dinosaurs that could adapt to these new environments could find ways to survive and reproduce effectively, spurring further evolution. Many species began to specialize, leading to a greater variety of shapes and sizes among dinosaurs, which correlated closely with their dietary preferences and living conditions. The rise of flowering plants during the Cretaceous period was not just a backdrop in the story of dinosaur evolution, it was a vital catalyst. As these plants diversified, they reshaped the ecosystems that dinosaurs inhabited, providing them with new dietary opportunities and habitats that drove competition, adaptation, and ultimately, the development of new dinosaur species. This intertwined evolution illustrates the dynamic relationship between flora and fauna, showcasing the intricate balance of life on Earth millions of years ago. The Cretaceous period, spanning from 145 million to 66 million years ago, was home to a rich diversity of dinosaurs, both carnivorous and herbivorous. Among the most prominent carnivores of this era was Tyrannosaurus rex, a giant predator renowned for its formidable size and powerful jaw. It roamed the landscapes of what is now North America and was equipped with keen senses and a massive skull filled with sharp teeth designed for crushing bone. Another notable carnivorous dinosaur was Velociraptor, smaller in stature but agile and cunning, often believed to have hunted in packs, giving it a cooperative edge over its prey. On the other side of the dietary spectrum were the herbivorous dinosaurs, which included a variety of fascinating species. The Triceratops, with its iconic 3 horns and large frill, was a formidable presence on the Cretaceous plains, likely using its impressive weaponry to fend off attackers. Additionally, the enormous sauropods, like Brachiosaurus, grazed on treetops, their long necks allowing them to reach vegetation high above the ground. These gentle giants played a crucial role in shaping their environment as they fed, influencing plant growth and seed dispersal. Interactions between carnivores and herbivores were driven by a delicate balance of predator and prey dynamics. The herbivores employed various strategies to evade predators. Some, like the iguanodon, possessed defensive adaptations, such as thumb spikes, to deter attacks. Others potentially roamed in herds, providing safety in numbers against the lurking dangers of fierce predators like the Allosaurus and Giganotosaurus, which stalked these prey animals with stealth and speed. Moreover, these interactions fostered an evolutionary arms race. As carnivores developed more effective hunting techniques and stronger physical traits, herbivores adapted in response, evolving better defenses and strategies to survive. This cyclical relationship exemplified the interplay of life during the Cretaceous, ultimately contributing to the rich tapestry of ecosystems that defined this incredible period in Earth's history. The legacy of these dinosaurs continues to captivate our imagination, reminding us of the dramatic and often perilous life that thrived millions of years ago. During the Cretaceous period, roughly 145 to 66 million years ago, the planet was teeming with a vast array of reptiles, each uniquely adapted to their environments. Among those, the marine reptiles, like mosasaurs and plesiosaurs, and the flying reptiles, known as pterosaurs, showcase remarkable distinctions from their terrestrial relatives. While dinosaurs dominated the land, these specialized reptiles evolved distinct features that allowed them to thrive in water and the skies. Among those, the marine reptiles, like mosasaurs and plesiosaurs, and the flying reptiles, known as pterosaurs, showcase remarkable distinctions from their terrestrial relatives. While dinosaurs dominated the land, these specialized reptiles evolved distinct features that allowed them to thrive in water and the skies. Marine reptiles, for instance, developed streamlined bodies to navigate the oceans efficiently. Their limbs transformed into flippers, which enhanced their swimming capabilities, allowing them to become powerful predators in the sea. These creatures possessed adaptations such as elongated necks and sharp teeth, perfect for catching fish and other marine animals. In contrast, their terrestrial relatives, the dinosaurs, primarily relied on strong limbs for support and mobility on land, leading to a variety of shapes and sizes. Some dinosaurs, like the massive sauropods, utilized their long necks to reach high vegetation, while predators like the Tyrannosaurus rex relied on speed and strength. Flying reptiles took evolution in another intriguing direction. Unlike birds, which would later emerge, pterosaurs developed a wing structure that consisted of a membrane of skin and muscle stretched between an elongated fourth finger and their bodies. This unique adaptation allowed them to soar through the skies, hunting for fish and other prey. Their lightweight bones and extensive wingspans gave them the ability to glide efficiently, a feature that distinguishes them from their land-bound relatives who had to develop different means of locomotion and survival. In addition to these physical distinctions, the lifestyles of marine and flying reptiles contrasted with the more diverse behaviors seen among land dinosaurs. While some dinosaurs were solitary creatures, others traveled in herds. In the ocean and the skies, however, the marine and flying reptiles developed hunting and survival strategies that were tailored to their environments, showcasing the fascinating interplay of evolutionary pressures over millions of years. This diverse array of adaptations highlights the remarkable evolutionary paths taken by these extraordinary reptiles during the Cretaceous, illustrating the dynamic and changing world of ancient Earth. The social behavior of dinosaurs has intrigued paleontologists for many years, leading to significant discoveries about how these ancient creatures lived and interacted with one another. Fossil evidence is one of the most compelling sources of information. By studying dinosaur bone beds, where numerous individuals of the same species have been found together, scientists have begun to piece together the social dynamics of these prehistoric animals. For instance, large groups of dinosaurs, such as hadrosaurs, indicate possible herding behavior, similar to the way modern-day grazing animals congregate for protection and resource access. Fossils also provide insights through their physical characteristics. Some species, like the famous Tyrannosaurus rex, show signs that suggest social behavior might have been more complex than merely solitary hunting. Certain skeletal formations indicate that young T-Rex may have lived in groups, possibly for better chances of survival during vulnerable stages of life. Meanwhile, evidence from pack hunting behavior has been suggested in other theropods, like the velociraptor. This has sparked discussions about how these dinosaurs might have coordinated their efforts in hunting and protecting their young. Additionally, the discovery of nests offers another layer of understanding. Paleontologists have found dinosaur nests with multiple eggs laid in close proximity, hinting at parental care and communal nesting habits. Some species, such as Maiasaura, even show evidence of adults taking care of their young, further emphasizing social bonds. These findings challenge earlier assumptions that dinosaurs were entirely solitary creatures and highlight the complexity of their social structures. Moreover, trace fossils like trackways can provide real insight into how dinosaurs moved together. Fossilized footprints indicate instances where several individuals walked and ran side by side. These trackways often suggest that herding behavior was common among many species, reinforcing the idea that social structures played a significant role in the life of dinosaurs. As new discoveries emerge, our understanding of their social behaviors continues to evolve, revealing the rich tapestry of interactions within these remarkable creatures. The evolution of dinosaur communication is a fascinating aspect of paleontology that sheds light on the social behavior and ecology of these ancient creatures. Dinosaurs, like modern birds and reptiles, likely developed various methods to communicate, driven by social needs such as mating, herd dynamics, and territoriality. These forms of communication would have evolved over millions of years, adapting to the specific environmental and social pressures faced by different dinosaur species. One of the most compelling theories suggests that vocalizations played a significant role in how dinosaurs communicated. Just as some present-day birds use complex songs to attract mates or warn of danger, dinosaurs could have produced sounds ranging from simple calls to elaborate vocal displays. Fossilized evidence hints that certain dinosaur skulls had the anatomical capacity for producing low-frequency sounds, which could travel long distances, allowing them to communicate across vast expanses of their habitat. In addition to vocal sounds, body language would have been a crucial part of their communicative repertoire. Dinosaurs could have used visual cues, such as posturing, tail movements, or coloration, to convey messages to one another. Some species, particularly those known from fossilized feathers or patterns on their skin, may have relied on vivid displays during courtship or competition for mates. This suggests that dinosaurs might not only have communicated through sound, but also through the visual spectacle of their bodies. It's also possible that tactile communication was employed, especially among social species. Behaviors such as nuzzling or nudging could have expressed affection, aggression, or submission within groups of dinosaurs. As researchers continue to study the fossil record and modern analogues, our understanding of how dinosaurs communicated will likely deepen, revealing a rich tapestry of interactions that paints a more complete picture of life during the Mesozoic era. Parental care is a fascinating aspect of the lives of dinosaurs that greatly influence the survivability of their young. While traditional images of dinosaurs often depict them solely as fierce predators or lumbering giants, evidence increasingly suggests that many species exhibited various forms of parental investment. This care could have taken several forms, from incubation of eggs to protecting young from predators. Nest building is one of the key behaviors indicating that some dinosaurs invested time and effort in their offspring. Fossilized nests have been discovered, showcasing eggs arranged in a protective manner. Some of these nests show signs of having had adults present, indicating a level of protection. For example, there is evidence that certain species, such as the well-known hadrosaurs, may have shielded their nests from environmental dangers or predators, increasing the chances of hatchling survival. Moreover, there are indications that some dinosaur species might have cared for their young after they hatched. Fossil evidence suggests that hadrosaurs and theropods, like Oviraptor and Troodon, possibly helped their young find food and offered protection. This nurturing behavior likely improved the chances of survival, allowing the hatchlings to grow strong enough to fend for themselves in a world filled with peril. Understanding the role of parental care in dinosaurs not only illuminates their behaviors, but also provides insights into their social structures and interactions. While many aspects of their lives remain shrouded in mystery, the discovery of parenting behaviors opens windows into how these magnificent creatures thrived in their prehistoric environment, contributing to the continuation of their species for millions of years. Dinosaurs roamed the Earth during a time when the planet was strikingly different from today. They inhabited various major terrestrial habitats, each distinct in flora, climate, and geology. Among these, lush forests, arid deserts, and expansive plains stood out as key environments. These habitats played crucial roles in shaping the lives and adaptations of dinosaurs, influencing everything from their size and shape to their behavior and feeding strategies. In the tropical regions, vast coniferous and angiosperm forests provided rich ecosystems filled with towering trees and diverse plant life. These dense forests sheltered many herbivorous dinosaurs, which thrived on the abundant vegetation. Member species like the enormous sauropods developed long necks to reach the treetops, while smaller dinosaurs, such as the agile theropods, hunted in the underbrush. This rich plant diversity fostered an intricate web of life, where the balance between predator and prey influenced evolutionary adaptations. Contrasting these lush forests, the arid deserts of the Mesozoic era presented a harsher living environment. These dry regions likely hosted dinosaurs that could tolerate extreme conditions, showcasing adaptations like water retention and burrowing behavior. Dinosaurs such as the horned dinosaur species likely utilized these habitats for nesting, using the sparse vegetation and open land to evade potential predators. Deserts also support fossils that give insight into the animal's survival strategies in a resource-scarce setting. Expansive floodplains and coastal environments contributed to another layer of diversity. These zones, frequently shaped by ancient rivers and changing sea levels, provided rich alluvial soils for plant growth, attracting various plant-eating dinosaurs. Meanwhile, the proximity to water sources meant that these habitats also harbored aquatic dinosaurs and other reptiles, creating complex ecosystems where multiple species interacted. This variety of environments across the globe contributed to a fascinating mosaic of life during the age of dinosaurs, each adapting uniquely to their surroundings while sharing the Earth for millions of years. Dinosaurs roamed a diverse array of ecosystems, each shaping their lifestyles in unique ways. During the Mesozoic era, which spanned over 160 million years, the Earth's climate was typically warmer and more humid, fostering rich vegetation. This lush flora provided ample food sources across vast landscapes. The types of plants varied significantly over time, from the towering cycads and ferns of the Triassic period to the cone-bearing gymnosperms and eventually the flowering angiosperms in the Cretaceous period. Each of these plant groups contributed to the dietary needs of dinosaurs, accommodating both herbivorous and carnivorous species. Herbivorous dinosaurs, such as Brachiosaurus and Stegosaurus, thrived in this thriving plant life, utilizing their adaptations to reach high vegetation or graze on lower shrubs. Their large size helped them consume vast amounts of plant material every day. Meanwhile, the appearance of flowering plants toward the end of the Mesozoic created new food sources that influenced the evolution of herbivores. Some species developed specialized features to feast on these new plants, which, in turn, supported an intricate food web that included the carnivorous dinosaurs that preyed upon them. However, the flora posed challenges as well, particularly through competition and toxicity. Some vegetation produced chemical defenses to deter herbivores. This means that not all available food was safe to consume, forcing dinosaurs to adapt their diets and foraging behaviors. Additionally, the dense forests could also present obstacles for movement, forcing some species to develop agility in navigating complicated terrains, while others, like the large sauropods, simply relied on their size to dominate the landscape. Fauna also played a critical role in these ecosystems. The presence of various small reptiles, mammals, and other dinosaurs created a complex tapestry of life that influenced survival strategies. Dinosaurs had to contend with evolving predators, adapt to the varying availability of prey, and even scavenge when faced with food shortages. In these dynamic environments, competition and adaptation were essential for thriving, highlighting a constant interplay between the flora and fauna that shaped the lives of dinosaurs for millions of years. The evidence of predator-prey dynamics among dinosaur species and their contemporaries is rich and diverse, stemming from a variety of sources. One of the most fascinating pieces of evidence comes from fossilized remains found in what were once bustling ecosystems. Paleontologists have discovered dinosaur bones that show signs of predation, such as bite marks or puncture wounds, which suggest that certain dinosaurs hunted others for food. These fossilized interactions provide a direct glimpse into the complex relationships between species in the Mesozoic era. Additionally, coprolites, or fossilized dung, serve as another vital source of information about these dynamics. Through the analysis of coprolites, scientists can determine what dinosaurs were eating, revealing a spectrum of prey animals. Some coprolites contain bone fragments, indicating that larger carnivorous dinosaurs consumed smaller relatives or other creatures within their environment. This not only allows researchers to reconstruct dietary habits, but also illuminates the role of different species within their ecosystems. Another compelling piece of evidence comes from trackways, which are impressions left behind by dinosaurs as they walked or ran. In some sites, tracks of large predatory dinosaurs have been found alongside those of smaller herbivores. The arrangement of these tracks often suggests that predators were actively stalking or pursuing their prey. By studying these patterns, scientists can infer behavioral aspects and interactions that might have played out millions of years ago. Finally, the abundance of diverse dinosaur species in certain fossil beds paints a broader picture of predator-prey relationships. Ecosystems inhabited by various dinosaurs show how these creatures coexisted, competed, and interacted. By understanding the sizes, shapes, and hunting techniques of different species, researchers can reconstruct ancient food chains and understand the ecological balance of these prehistoric worlds, highlighting the intricate web of life that once thrived on Earth. Dinosaurs, the remarkable creatures that roamed the Earth during the Mesozoic era, were characterized by a variety of distinctive physical adaptations that allowed them to thrive in their environments. One of the most notable adaptations was their diverse body size and shape. From the towering Brachiosaurus, which could reach heights of up to 80 feet, to the nimble Velociraptor, these adaptations allowed dinosaurs to exploit different niches. Large body sizes provided defense against predators and the ability to reach high vegetation, while smaller, agile forms allowed for swift movement and effective hunting. Additionally, the evolution of bipedalism in some species, particularly theropods, gave rise to a new way of handling the environment. Walking on two legs freed up the front limbs for other tasks, including grasping prey or manipulating objects. This adaptation not only improved mobility, but also facilitated a varied diet. As a result, theropods could become adept hunters, while some other dinosaur lineages developed into herbivorous giants, showcasing a fascinating specialization based on their feeding habits. Another significant adaptation was the development of specialized teeth and jaws. Herbivorous dinosaurs like the Stegosaurus and Triceratops evolved flat, grinding teeth suited for breaking down tough plant material, while carnivorous types like the Tyrannosaurus rex possessed sharp, serrated teeth designed for tearing flesh. This diversity in dentition reflects the evolutionary pressures of competing for food and adapting to available resources in various ecosystems. Dinosaurs also exhibited unique features like armor and crests. Many species had protective plates or spikes, such as the Stegosaurus with its characteristic bony plates along its back. These features offered not just defense against predators, but also possibly served display purposes during courtship or territorial disputes. By combining these distinct adaptations, dinosaurs demonstrated an incredible ability to dominate the landscapes of the Mesozoic era, ultimately leading to their status as one of the most successful groups of animals in Earth's history. Dinosaurs were incredibly diverse creatures, each uniquely adapted to their environments. Their success during the Mesozoic era, which spanned over 160 million years, is attributed largely to their distinct physiologies. For instance, many dinosaurs had specialized adaptations, such as intricate respiratory systems that allowed them to thrive in varying climates. Some even exhibited advanced social behaviors, enabling them to cooperate in herds for protection against predators and for nurturing their young. The variations in size, diet, and locomotion across different species played a crucial role in their ability to occupy numerous ecological niches. These unique adaptations not only allowed dinosaurs to dominate land ecosystems, but also helped them evolve into some of the most formidable predators and successful herbivores of their time. For example, the massive, long-necked sauropods could reach high into trees to feed on foliage that was inaccessible to other animals. Meanwhile, the smaller, fleet-footed dinosaurs had the agility to navigate complex terrains, evading larger predators and utilizing various food sources. This adaptability made dinosaurs nearly unstoppable for millions of years. However, these very characteristics that allowed dinosaurs to thrive also contributed to their eventual decline. The dramatic environmental changes at the end of the Cretaceous period, including shifts in climate and catastrophic events like the infamous asteroid impact, created stresses that many species could not withstand. The food chains that had supported diverse dinosaur populations began to unravel, leading to a cascade of extinctions. Dinosaurs, despite their remarkable adaptations, faced insurmountable obstacles that they had little chance to overcome. In the face of rapid and severe changes to their habitats, the specialized physiologies that once provided evolutionary advantages became liabilities. Larger species struggled to find suitable food sources as their forests and plant life dwindled. Similarly, epic climate shifts and volcanic activity altered environments too quickly for many dinosaurs to adapt, leading to their extinction roughly 66 million years ago. Through this lens, we can see that the success of dinosaurs was tied closely to their unique biologic adaptations, but the very foundation of that success ultimately contributed to their downfall. Mimicry and camouflage were critical strategies for the survival of various dinosaur species, helping them to navigate a world full of predators and competitors. These adaptations allowed some dinosaurs to blend seamlessly into their environments or imitate other animals, enhancing their chances of evading predation. For instance, dinosaurs that exhibited skin patterns similar to their surroundings could conceal themselves from hungry predators. This ability to hide among the foliage or blend into rocky terrains could mean the difference between life and death. Mimicry also played a role in the survival of certain species. Some dinosaurs might have displayed colors or patterns that mimicked the appearance of more dangerous or toxic species, deterring potential threats. This tactic not only reduced the chance of being targeted as prey, but also provided a strategic advantage over rival species vying for the same resources. By mimicking these features, these dinosaurs could exploit the survival mechanisms of more formidable creatures, helping them thrive in their ecosystems. Additionally, these adaptations extended beyond mere survival tactics. They could also influence social interactions within species. Dinosaurs might have used colors and patterns for communication, aiding in attracting mates or asserting dominance. In some cases, the vivid colors might serve as a warning signal to others, conveying vital information about their health or reproductive status. This combination of mimicry and camouflage illustrates the complexity of dinosaur behavior and the ecological pressures they faced. Ultimately, the roles of mimicry and camouflage underscore the breathtaking diversity and adaptability of dinosaur species. As these ancient creatures roamed the Earth, their ability to blend into their surroundings or imitate others not only enhanced their survival, but also shaped the intricate web of life that existed during the age of dinosaurs. Understanding these strategies allows us to appreciate how these remarkable animals thrived in a dynamic and often perilous world. The extinction of the dinosaurs, approximately 66 million years ago, remains one of the most fascinating mysteries in Earth's history. The prevailing theory centers around a catastrophic event, specifically a massive asteroid impact. This hypothesis gained significant traction after scientists discovered a layer of iridium-rich clay in the geological record, particularly at the boundary marking the end of the Cretaceous period. Iridium is rare on Earth but abundant in asteroids, leading to the conclusion that a celestial body struck the planet, creating the Chicxulub crater in present-day Mexico. Alongside the asteroid impact hypothesis, another leading theory points to extensive volcanic activity, particularly in what is now the Deccan Traps in India. This volcanic region experienced massive eruptions, releasing enormous volumes of lava and gases such as sulfur dioxide and carbon dioxide into the atmosphere. Such an outpouring would have significantly altered the climate, producing acid rain and initiating a greenhouse effect that could have led to drastic temperature changes. Evidence from rock layers suggests that these eruptions coincided with the period of the dinosaurs' extinction, bolstering the volcanic hypothesis. Interestingly, some researchers propose that both the asteroid impact and volcanic activity may have acted synergistically. The asteroid strike could have caused immediate devastation through shock waves, fires, and tsunamis, which would have led to short-term climatic changes. Concurrently, the ongoing volcanic eruptions could have exacerbated these effects, creating a prolonged environmental crisis that made survival increasingly difficult for dinosaurs and other species. This combined scenario helps explain the relatively rapid extinction event observed in the fossil record. While both the asteroid and volcanic activity theories have solid scientific backing and substantial evidence, researchers continue to explore alternative factors. Habitat loss, changing sea levels, and climate fluctuations might have also contributed to the broader stresses the dinosaurs faced during this period. Although the evidence for the impact and volcanic hypotheses remains the most compelling, the ongoing research in this area keeps the discussion vibrant, underscoring the intricate interplay of natural forces at work in shaping our planet's history. The impact event theory, which suggests that a cataclysmic collision between Earth and a celestial object, such as an asteroid or comet, can cause significant extinction events, gained prominence in the late 20th century. This theory was significantly influenced by the discovery of a layer of iridium-rich clay in the geological record, particularly noted in a site in Italy called Gubbio. This layer dates back to about 65 million years ago and corresponds with the mass extinction event that wiped out the dinosaurs, leading scientists to suspect a link between the two occurrences. The iridium anomaly served as vital evidence since iridium is rare on Earth but abundant in asteroids and comets. Further investigations revealed a distinctive circular structure known as the Chicxulub crater, located on the Yucatan Peninsula in Mexico. This crater measures over 180 kilometers in diameter and is believed to have formed around the same time as the extinction event. Such findings led scientists to propose that a massive object, perhaps about 10 kilometers wide, collided with Earth, generating immense heat and devastating environmental consequences. In addition to geological evidence, the impact event theory is supported by research into the effects of impacts on ecosystems. Studies of present-day impact craters have shown that such collisions can lead to wildfires, tsunamis, and a prolonged impact winter, a period of darkness and cooling resulting from debris obscuring sunlight. These scenarios help illustrate how a sudden event could drastically alter climates and habitats, contributing to mass extinction. More recent discoveries of other impact sites, paired with ongoing studies of the fossil record, continue to strengthen the theory. The correlation between impact events and periods of mass extinction, both in Earth's past and potentially in the future, highlights the significance of these cosmic encounters in shaping life on our planet. As we unearth more evidence, the narrative of Earth's history continues to evolve, revealing how our planet is interconnected with the broader cosmos. The Deccan Traps, a vast volcanic province in India, play a fascinating role in the story of Earth's history. Around 66 million years ago, this region experienced an extraordinary series of volcanic eruptions that released an immense volume of lava and gases into the atmosphere. These eruptions continued over thousands of years, creating massive basalt layers, but also significantly altering the environment. One of the primary ways the Deccan Traps may have contributed to the extinction event is through the release of sulfur dioxide and carbon dioxide into the air. Sulfur dioxide can lead to acid rain, which harms plant life and disrupts ecosystems. The resulting decline in vegetation would also have triggered a cascade effect, affecting herbivores and, subsequently, the carnivores that preyed on them. A significant reduction in plant life would have virtually changed the face of terrestrial ecosystems, making it difficult for many species to survive. Simultaneously, the carbon dioxide emitted during these eruptions likely contributed to a long-term greenhouse effect. Rising temperatures could have altered climatic conditions worldwide. As the climate shifted, habitats changed, putting additional stress on species already struggling due to habitat loss and food shortages. The combination of cooling temperatures from the atmospheric particles and warming from greenhouse gases created an unstable environment, which is not the kind of place where many species can thrive. The volcanic activity of the Deccan Traps thus presents a compelling case for how natural events can drive mass extinction. The eruptions occurring in tandem with the infamous asteroid impact at Chicxulub likely created a perfect storm of environmental upheaval. The cumulative impact of these factors represents a stark reminder of how interconnected our planet's systems are and how swiftly they can shift in the face of large-scale geological events, ultimately leading to the demise of a vast array of life forms. Paleontologists play a crucial role in uncovering, preserving, and interpreting the history of dinosaurs through the study of fossils. The process often begins with fieldwork, where these scientists trek to locations known for rich fossil beds, such as remote deserts or cliff faces. They carefully examine the rock formations, looking for telltale signs of fossilized remains. Once a potential site is found, paleontologists will gently excavate the area with tools like brushes and chisels, revealing the bones buried in the earth. Once a fossil is uncovered, the next important step is preservation. Paleontologists often use specialized techniques to protect the fossils from damage during the extraction process. This can include using plaster jackets to stabilize fossils for transport. Back in the laboratory, they may use chemical treatments to clean and preserve the fossils, ensuring they remain intact for future study. The goal is to maintain as much of the original structure and material as possible, as this provides valuable data for scientific interpretation. Interpreting the fossils is where the real detective work begins. Paleontologists analyze the bone structure, size, and any unique features to determine the species and its characteristics. They often compare fossils with those from related species to understand their evolution, behavior, and environmental adaptations. Advanced technology, including X-ray imaging and computer modeling, helps scientists visualize the physiological traits of these ancient creatures, further refining their understanding of how dinosaurs lived. Through this meticulous process of uncovering, preserving, and interpreting fossils, paleontologists piece together the story of Earth's distant past. Each discovery adds a new chapter to our understanding of life during the age of dinosaurs, illuminating not only the creatures themselves, but also the ecosystems they inhabited. This ongoing exploration continues to inspire curiosity about our planet's prehistoric inhabitants and their enduring legacy. Throughout the years, several dinosaur fossil discoveries have fundamentally changed our understanding of these ancient creatures, each adding a unique piece to the puzzle of how dinosaurs lived, evolved, and interacted with their environment. One of the most significant finds was the discovery of feathered dinosaur fossils in the late 20th century. These fossils, primarily unearthed in China, have provided compelling evidence that birds are indeed a living lineage of dinosaurs. This revelation has transformed our perspective, showing that feathers, once thought exclusive to birds, may have been prevalent among various dinosaur species, possibly for insulation, display, or even gliding. Another groundbreaking discovery was the fossilized remains of a creature named Archaeopteryx. Often referred to as the first bird, this transitional fossil showcases a blend of features from both dinosaurs and modern birds, like wings with feathers and a long, bony tail. Found in Germany in the late 19th century, Archaeopteryx has served as critical evidence in the study of evolution, highlighting the connection between reptiles and birds and pointing to the origin of flight as a more complex process than previously understood. The find of the impressive skeleton of T. rex in the early 20th century also had a dramatic impact on our understanding of dinosaur anatomy. Discoveries of more complete T. rex fossils have allowed scientists to deduce not just how this behemoth stood and moved, but also what it might have hunted and how it interacted with its environment. With advancements in imaging technology, researchers are now delving deeper into these fossils, revealing insights into the dinosaurs' musculature and lifestyle that were unimaginable just a generation ago. Finally, the recent discovery of hadrosaur fossils with intact skin and potential evidence of color patterns has opened an exciting chapter in paleontological research. This suggests that some dinosaurs might have had complex social behaviors and mating displays similar to modern animals. Each of these discoveries reflects a continuous evolution in our understanding of dinosaurs, pushing the boundaries of what we thought we knew about these magnificent creatures and their place in Earth's history. Fossilized tracks and nests offer a remarkable window into the daily lives of dinosaurs, revealing not only how they moved, but also their social behaviors and nesting patterns. These tracks, often preserved in sedimentary rock, can tell us about the size, speed, and direction of dinosaurs as they walked or ran. For instance, the spacing of the footprints can suggest whether a dinosaur was moving slowly and casually or in a hurried flight, perhaps fleeing from a predator. Moreover, the arrangement of tracks can reveal insights about dinosaur herding behavior. Larger groups of footprints may indicate social structures similar to how modern animals travel in packs or herds for safety or social interaction. In some cases, researchers have also found overlapping tracks from different species in the same area, suggesting the possibility of communal living or shared resources among dinosaurs. When it comes to nesting, fossilized nests provide invaluable clues about reproduction and parental care. Discoveries of nests containing eggs can show us the types of animals that laid them and hint at their nesting habits. Some nests have been found in clusters, which may indicate that dinosaurs returned to the same site to lay eggs, suggesting a level of loyalty to their breeding grounds. Additionally, the study of these nests and tracks can help paleontologists understand climate and environmental conditions during the time of the dinosaurs. For example, certain nesting behaviors may indicate specific temperatures or seasons, providing a broader picture of the ecosystems in which these magnificent creatures lived. Together, fossilized tracks and nests create a narrative of dinosaur life, one that combines behavioral ecology with the natural history of our planet. While the world often celebrates famous dinosaurs like Tyrannosaurus rex and Triceratops, there exists a plethora of lesser-known yet equally captivating species that roamed our planet millions of years ago. One such example is the Therizinosaurus. This herbivorous dinosaur stood out not only for its immense size, reaching lengths of up to 40 feet, but also for its strikingly long claws, which could be over a foot in length. These claws, perhaps used for foraging or defense, give us a glimpse into the unique adaptations that dictated its lifestyle in a world dominated by more predatory species. Another intriguing dinosaur is the Velociraptor, often overshadowed by its more famous portrayal in popular media. In reality, these creatures were about the size of a turkey, with feathers that likely aided in display and possibly even temperature regulation. Velociraptors were agile predators, equipped with a distinctive sickle-shaped claw on each foot, enabling them to swiftly hunt smaller prey. Their social behavior, likely hunting in packs, challenges our perception of these small dinosaurs as solitary creatures. Don't overlook the iguanodon, a dinosaur that played a vital role in early dinosaur research. It was one of the first dinosaurs to be named and identified, contributing significantly to our understanding of these ancient creatures. Iguanodon had a unique thumb spike that evolved to aid in defense and foraging. This dinosaur also exhibited fascinating social behaviors, with evidence suggesting that it might have traveled in herds, showcasing a social aspect to its life that we are still piecing together. Lastly, let's consider the enigmatic Ankylosaurus, known for its heavily armored body and club-like tail. This dinosaur was essentially a walking fortress, designed to deter predators with its tough, bony plates and sharp spikes. Such adaptations reflect the fierce survival strategies needed during the late Cretaceous period. Together, these lesser-known dinosaurs provide a broader view of the diversity and complexity of life during the Mesozoic era, inviting us to explore the nuances of evolution and survival that shaped our planet long before humans walked on it. Throughout the ages, dinosaurs roamed our planet, exhibiting incredible diversity. However, some species remain largely unseen in the paleontological record, leaving scientists with more questions than answers. One reason for this obscurity is the rarity of fossilization itself. Most organisms decompose after death, and fossilization requires a very specific set of conditions. For a dinosaur to become a fossil, it must be buried rapidly in sediment, a scenario that doesn't happen often. Consequently, it is possible that many species simply never became fossils at all. Another critical factor in this mystery is the sheer volume of dinosaurs that existed over millions of years. While some species, like the towering Tyrannosaurus rex, have been discovered in great numbers, many smaller or less dominant dinosaurs may have left behind fewer remains. In a chaotic ecosystem, the larger and more predatory species tend to be better represented, overshadowing others. This imbalance can create a skewed understanding of diversity, leading to the belief that more than one species may have simply vanished without recognition. Geographic and environmental factors also play a significant role. Dinosaurs lived in various ecosystems, with some regions more conducive to fossil preservation than others. Areas prone to erosion or changes in landscape may have obliterated the potential for future fossilization. As a result, species that occupied less favorable environments might have slipped through the cracks of time, their existence barely hinted at in the geological record. Lastly, ongoing advancements in paleontological techniques can lead to the revelation of new species and re-examination of past findings. As scientists explore previously inaccessible terrains or utilize cutting-edge technologies like imaging, they may uncover new fossil remains that challenge our existing understanding. This persistent quest for knowledge reminds us that while some dinosaur species may remain obscure, the possibility of discovering their secrets still exists. Each piece of evidence brings us one step closer to understanding the vast and intricate tapestry of life that once flourished in the age of dinosaurs. The advent of technology, particularly CT scanning and three-dimensional modeling, has profoundly transformed our understanding of dinosaur physiology and behavior. In the past, much of what we knew about dinosaurs came from fossilized bones that provided only a limited view of their anatomy. However, with the development of advanced imaging techniques, scientists can now look inside these fossils without damaging them. This non-invasive approach reveals details hidden within bone structures, allowing researchers to explore how dinosaurs lived, moved, and interacted with their environment. CT scanning allows for the creation of detailed cross-sectional images of fossilized remains. Through this process, scientists can analyze the internal features of bones, including blood vessel pathways and the arrangement of muscle attachment sites. Such insights lead to more accurate depictions of how strong or agile a dinosaur might have been. For example, researchers have uncovered that certain dinosaurs had complex air sacs within their bones, similar to modern birds, which could suggest a certain level of metabolic efficiency and respiratory adaptations long thought to be unique to avian species. Moreover, three-dimensional modeling enhances our ability to reconstruct these majestic creatures. Scientists can use the data gleaned from CT scans to build accurate virtual representations of dinosaurs. This allows for the testing of hypotheses about dinosaur movement and behavior in a way that was previously impossible. By simulating how different dinosaur species might have walked, run, or even interacted with each other, researchers can begin to piece together a more comprehensive picture of their ecology and social structures. These technological advancements not only enrich our understanding of individual species, but also help scientists better interpret the paleoecology of entire ecosystems. By examining how dinosaurs lived and behaved, we gain insights into the environmental factors that influence their evolution. Overall, the integration of CT scanning and 3D modeling in paleontology has opened a treasure trove of information, allowing us to appreciate the complexity and diversity of life during the age of dinosaurs in ways that were unimaginable just a few decades ago. Computer simulations are revolutionizing the way scientists understand the lives of dinosaurs, particularly their movement and interactions. By creating detailed models that embody the physical characteristics of various dinosaur species, researchers can simulate how these magnificent creatures would have behaved in their natural environments. This process involves integrating fossil evidence, anatomical data, and insights from modern animals to present a comprehensive picture of dinosaur life. One of the primary advantages of computer simulations is their ability to analyze the biomechanics of dinosaur movement. Scientists can test different locomotion scenarios to see how various factors, such as size, weight, and limb structure, affect the way these animals moved. For example, simulations can reveal insights into whether a large dinosaur could run, how it would maneuver through dense vegetation, or the speed at which it could sprint. This virtual experimentation helps clarify long-standing questions about their adaptability to changing environments and interactions with other species. Simulations also extend beyond just movement to explore social interactions among dinosaurs. Through sophisticated algorithms, researchers can model group behavior, whether it be herding, nesting, or combat. This not only sheds light on the social structures and relationships within these ancient species, but also how they communicated and competed for resources. Understanding these dynamics enhances our perspective on the ecosystems in which dinosaurs lived, providing context to their evolutionary development. Ultimately, computer simulations serve as a vital bridge connecting past and present. They allow paleontologists to visualize and experimentally engage with a world that existed millions of years ago. As technology progresses, these simulations will undoubtedly become even more detailed and informative, offering further insights into the lives of these extraordinary creatures and helping us piece together the vast puzzle of our planet's prehistoric history. The study of dinosaurs has provided invaluable insights into the processes of evolution and ecology, shaping our modern understanding of life's development on Earth. As scientists unearthed fossilized remains and studied the anatomy of these ancient creatures, they began to piece together the complex relationships among different species and their environments. Dinosaurs lived in a variety of ecosystems, from lush forests to arid deserts, and examining their adaptations helps us understand how species evolve in response to environmental challenges. One of the most significant contributions of dinosaur studies is the insight they provide into the concept of adaptive radiation. This phenomenon occurs when a single lineage diversifies into various forms, each adapted to a unique ecological niche. The dinosaurs exemplify this as they evolved into a myriad of shapes and sizes, demonstrating how environmental pressures can lead to the development of diverse traits. Such understanding informs our knowledge of how current species, including mammals and birds, may adapt or evolve in changing climates. Furthermore, studying the extinction of the dinosaurs has been crucial to our understanding of ecology and its resilience. The mass extinction event that occurred around 66 million years ago not only wiped out the dinosaurs, but also reshaped entire ecosystems. Investigating the aftermath of this event reveals how life can rebound and adapt, following dramatic ecological shifts, providing valuable lessons about biodiversity and ecosystem recovery that are relevant in today's climate crisis. Lastly, insights gathered from the behavior and social structures of dinosaurs, inferred from fossil evidence and modern analogues, continue to impact ecological theories. By exploring their potential parenting strategies, foraging behaviors, and social interactions, scientists can draw parallels to the behavior of contemporary species. This understanding enriches our appreciation of life's complexity and interdependence in ecosystems, reminding us that the principles of evolution and ecology are as relevant now as they were millions of years ago. Through the lens of dinosaurs, we gain a deeper understanding of the intricate tapestry of life that evolves and thrives on our planet. Birds, often overlooked in the grand tapestry of evolution, are direct descendants of dinosaurs. Their lineage traces back to theropod dinosaurs, the same group that included the notorious Tyrannosaurus rex. This fascinating connection means that many traits we observe in birds today echo features found in their ancient forebears, offering a living link to a time long past. One of the most striking similarities lies in skeletal structure. Birds possess a lightweight skeletal frame, which is remarkably similar to the bones of certain theropod dinosaurs. These adaptations allow for flight. For instance, the structure of a bird's forelimb has transformed into a wing, yet underneath it maintains a fundamental arrangement of bones reminiscent of those seen in dinosaur limbs. Additionally, features such as a flexible neck and a keeled breastbone, which supports powerful flight muscles, can be traced back to those earlier species. Feathered bodies also serve as a captivating reminder of their dinosaur ancestry. Initial discoveries of feathered dinosaurs in fossil records revealed that feathers originally developed for insulation or display, akin to modern bird behavior. Birds wear their feathers with pride, showcasing a spectrum of colors and patterns that play essential roles in mating rituals and camouflage, linking them back to their display behaviors in the Mesozoic era. Furthermore, behaviors such as nesting and brooding reflect traits that have persisted since the age of dinosaurs. Many modern birds exhibit care for their young, incubating eggs in intricate nests. This nurturing behavior is not merely instinctual. It signifies evolutionary ties to the caring habits observed in some dinosaur species. Thus, every chirp and flutter we witness in our feathered friends today serves as a captivating whisper from a bygone era, connecting us to the majesty of prehistoric life. When we think about dinosaurs and their legacy, many are surprised to learn that modern birds are their closest living relatives. This connection is not merely a fleeting resemblance. Over millions of years of evolution, certain traits have been preserved and refined in birds that can be traced back to those ancient creatures. The similarities in skeletal structure, feathers, and even some behaviors highlight an intricate link that reshapes our understanding of both birds and dinosaurs. In addition to birds, crocodilians, such as alligators and crocodiles, share a more distant yet significant relationship with dinosaurs. Both groups belong to a larger category known as archosaurs, which means ruling reptiles. This lineage split off millions of years ago, but still retains crucial characteristics that offer insights into the evolutionary path taken by many reptiles. For instance, the strong, robust build of crocodilians echoes some of the formidable traits seen in their prehistoric relatives. The evolutionary connections between these animals suggest a tree of life rich with branches that communicate stories of survival and adaptation. Dinosaurs did not simply vanish. The evolutionary journey continued, leading to the present-day birds that we hear chirping around us. This ongoing narrative illustrates how traits such as feathers and certain bone structures have persisted, solidifying birds' place as the modern embodiment of these ancient giants. Thus, when we observe birds soaring across the sky or crocodiles lurking in the waters, we are witnessing a living testimony to the dinosaur legacy. Their existence reminds us of the complex interplay of evolution and survival, revealing an intricate tapestry of life that stretches across millions of years, connecting us directly to a time when dinosaurs ruled the earth. Dinosaurs, those magnificent creatures that roamed the Earth millions of years ago, varied immensely in size and scale, showcasing astounding diversity. While the most well-known dinosaurs, like Tyrannosaurus rex, capture our imagination and attention, it's essential to remember that not all dinosaurs were colossal. Some, like the Compsognathus, were the size of a chicken, highlighting that the dinosaur era hosted a variety of sizes, just as today's ecosystems do. When we look at the largest dinosaurs, such as Argentinosaurus or Patagotitan, we see land animals that could reach lengths of over 100 feet and weighed tens of tons. To put that into perspective, the average weight of today's largest land animals, like elephants, ranges around 6 tons. While these modern titans are impressive, they dwarf in comparison to some of the massive sauropods from the prehistoric period. Imagine a creature so vast that it would be like trying to picture a building standing on its legs, reaching up to the treetops. In contrast to the large dinosaurs, today's land animals also include remarkably small species, much like their ancient relatives. For instance, many of today's small mammals, birds, reptiles, and even insects can be compared to the smaller dinosaurs, creating an intriguing parallel in terms of ecological niches and adaptations. Size isn't the only factor. Just as today's animals have adapted to various environments, urban areas, forests, and deserts, dinosaurs too evolved uniquely based on their habitats. It's fascinating to realize that while the Earth's largest inhabitants were so grand, dinosaurs represented the extremes of size in their ecosystems. As they existed in a world vastly different from ours, many of the size-related features we see in modern animals are shaped by the needs and challenges of their environments, creating an ongoing story of evolution through the ages. The legacy of these remarkable creatures, both great and small, continues to influence the wildlife we see today, reminding us of the ever-changing tapestry of life on our planet. Dinosaurs, the magnificent rulers of the Earth for over 150 million years, faced a variety of evolutionary pressures that shaped their development and survival. Among these pressures were environmental changes, resource competition, and predation. As the climate shifted and landforms transformed, dinosaurs had to adapt to diverse habitats and conditions. These challenges are not unlike what modern animals experience today, particularly as global climate change alters ecosystems. Competition for food and territory was another significant pressure. In the age of the dinosaurs, a plethora of species coexisted, each vying for resources. This competition necessitated adaptations like the development of specialized diets or social behaviors to better navigate their environments. Similarly, today's animals must contend with an ever-changing world where habitat loss and human activities disrupt their natural surroundings and influence survival strategies. Predation played an essential role in shaping dinosaur evolution as well. Many species developed greater size, protective features, or offensive capabilities to thwart threats posed by other predators. This dynamic of predator and prey continues to drive evolution among modern species. For instance, many animals develop camouflage or heightened senses to evade or escape predators, just as dinosaurs likely did. Finally, diseases and parasites were also significant pressures that influenced the survival of dinosaurs. As they thrived in diverse ecosystems, they became susceptible to various pathogens, leading to the evolution of immune responses. In today's world, animals continue to face similar threats as they adapt to evolving diseases and parasites in their environments. Understanding these pressures offers a thrilling glimpse into the challenges faced by both ancient and contemporary life on Earth. The depiction of dinosaurs in ancient myths and legends reveals fascinating insights into how prehistoric life shaped human imagination. Though most dinosaurs lived millions of years before humans, the discovery of their bones and large fossils inspired various myths that reflected the power and mystery attributed to these ancient creatures. Across different cultures, tales often emerge that seem to echo the existence of giants, reptiles, and fearsome beasts, though they may not have directly referenced dinosaurs as we understand them today. In ancient cultures, such as those in Mesopotamia, large fossilized bones were sometimes interpreted as the remains of mythical creatures. For instance, in the epic tales of Gilgamesh, there are descriptions of gigantic beings and monsters that could be reminiscent of dinosaur-like creatures. Similarly, in the ancient Americas, the fossil bones discovered by native populations may have inspired legends about great serpents or colossal beings that roamed the earth, reflecting the awe and intimidation that these strange remains invoked. The dragons found in Chinese mythology are another intriguing example. These legendary creatures often bear resemblance to large reptiles, exhibiting characteristics that might evoke the image of terrestrial dinosaurs. Chinese dragons symbolize power and strength and represent an important part of cultural heritage. Myths about dragons could have originated from encounters with large dinosaur fossils, leaving lasting impressions that morphed into enduring legends. These stories not only showcase the creativity of human storytelling, but also highlight our innate curiosity about the natural world. The myths and legends inspired by dinosaur bones serve as a bridge between ancient cultures and the deep history of life on Earth, reminding us that even the most magnificent creatures of the past continue to shape our beliefs and narratives thousands of years later. As we reflect on these ancient tales, we can appreciate the enduring connections between our cultural heritage and the wonders of prehistoric life. Dinosaurs have left an indelible mark on modern media, literature, and pop culture, captivating audiences of all ages for generations. Their influence began in the 19th century when discoveries of fossils sparked public fascination. As these prehistoric giants became more recognizable, their stories found homes in literature, first appearing in the works of authors like Sir Arthur Conan Doyle, whose novel The Lost World presents a thrilling narrative featuring a living dinosaur in an isolated jungle. This early depiction set the stage for a myriad of stories that combined adventure with scientific discovery, turning dinosaurs into symbols of mystery and excitement. As cinema rose in popularity, dinosaurs became a favorite subject for filmmakers. The release of King Kong in the 1930s showcased the giant creatures within a fantastical narrative, but it was in the 1990s that dinosaurs truly roared to the forefront of pop culture. With the groundbreaking success of Jurassic Park, directed by Steven Spielberg, dinosaurs transitioned from the realm of dusty fossils to vibrant, lifelike beings brought to life through cutting-edge effects. The film's impact was monumental, leading to sequels and an entire franchise that not only entertained millions, but also reignited scientific interest in paleontology. It underscored how dinosaurs could bridge the gap between hard science and thrilling entertainment. Aside from film, dinosaurs have claimed their space in television, video games, and merchandising. Many animated series and children's programs have embraced these creatures, using them to educate and entertain young audiences, ensuring that the fascination continues to evolve. From the popular show Barney and Friends, which taught valuable life lessons through a friendly purple dinosaur, to the intricate video games that let players explore prehistoric worlds, dinosaurs' adaptability within media has made them timeless icons. Additionally, dinosaur-themed toys and merchandise have created a booming market, cementing their status as beloved figures in childhood culture. In literature, dinosaurs also remain prominent. They have inspired a range of genres, from horror and fantasy to educational texts, encouraging both children and adults to explore science through stories of survival and competition. Notable authors continue to write about them, blending facts with fiction to incite curiosity about our planet's distant past. Overall, the influence of dinosaurs on modern media, literature, and pop culture reflects our innate curiosity about life that existed millions of years ago, retaining their position as symbols of wonder and adventure that transcend time and continue to engage our imaginations. Dinosaurs hold a unique and significant place in modern educational settings, captivating the imaginations of students and educators alike. These ancient creatures, which roamed the Earth millions of years ago, provide a remarkable gateway into the study of biology, geology, and even history. As educators introduce the topic of dinosaurs, they not only engage students with powerful stories of life forms that once dominated our planet, but also inspire curiosity about evolution and extinction. One of the reasons dinosaurs captivate our imaginations is their sheer size and diversity. From the towering Brachiosaurus to the swift Velociraptor, these beings were unlike any animals we see today. This awe-inspiring diversity prompts questions about how these creatures lived, adapted, and ultimately vanished from the Earth. The use of dinosaurs in classrooms often utilizes vivid illustrations, models, and even interactive simulations, making the learning experience dynamic and memorable. Additionally, dinosaurs help convey scientific principles in an easily relatable manner. The processes of natural selection, adaptation, and fossilization become more tangible when linked to these fascinating beings. Students can explore concepts such as ecosystems and extinction events, gaining an understanding that transcends the distant past and relates to current environmental challenges. Through this lens, dinosaurs serve not just as objects of fascination, but as important figures in teaching resilience, adaptation, and the complexities of Earth's history. Moreover, the cultural impact of dinosaurs extends beyond academic settings. Movies, books, and toys featuring these majestic creatures create a shared reference point that fosters discussion and engagement in various contexts. This media presence allows the lessons learned in classrooms to seep into everyday life, making dinosaurs a continuous source of fascination. As we explore the legacy of dinosaurs, we open doors to understand our planet's past while encouraging future generations to ponder the mysteries of life on Earth. Paleoart, the artistic representation of prehistoric life, has played a crucial role in shaping our understanding and imagination of dinosaurs. This unique blend of art and science conveys the appearance, behavior, and environment of these ancient creatures in a way that text alone often cannot achieve. By visualizing what dinosaurs might have looked like, how they moved, and their interactions with one another and their surrounding ecosystems, paleoart brings the distant past into vibrant focus. For generations, artists have collaborated with paleontologists to create works that are both scientifically informed and visually compelling. These illustrations reflect the latest discoveries in paleontology and allow viewers to grasp the scale and diversity of dinosaur life. With each new find, be it a fragment of bone or a complete skeleton, paleoartists reimagine these creatures, resulting in a rich tapestry of interpretations that can vary dramatically, from feathered forms to more traditional, scaly depictions. Additionally, paleoart serves an important educational purpose. It captivates the imagination of young and old alike, making dinosaurs a symbol of scientific inquiry and discovery. Exhibits in museums often feature large, lifelike reconstructions that encourage curiosity and foster a deeper understanding of these ancient beings. Through these representations, we can better appreciate the evolutionary journey that has led from dinosaurs to modern birds. As our understanding of paleobiology evolves, so too does paleoart. The ongoing discoveries, such as the realization that many dinosaurs had feathers and vibrant colors, challenge previous misconceptions and inspire new works of art. This ongoing dialogue between science and art continues to enhance our interpretations of prehistoric life, reminding us that our understanding of the past is always expanding and evolving. Paleoartists play a vital role in our understanding of prehistoric life, blending science and creativity in fascinating ways. Their task goes beyond mere illustration. It requires a deep understanding of paleontology, anatomy, and the environment of ancient ecosystems. By studying fossil evidence, including bone structure and footprint patterns, these artists form a base of scientific accuracy. They collaborate closely with paleontologists and rely on the latest research findings to make sure their depictions are not only visually striking, but also reflect the most current understanding of extinct species. However, the world of prehistoric life is often shrouded in uncertainty. Fossil remains can sometimes offer limited information, leaving gaps that require artistic interpretation. For instance, the skin color of dinosaurs is mostly unknown, as color pigments do not typically fossilize. Here, artists exercise creative freedom, drawing on existing wildlife for inspiration. Just as modern birds exhibit a range of colors and patterns, paleoartists may choose to depict dinosaurs in vibrant hues to make them more engaging. This blending of fact and interpretation is crucial for capturing the imagination of audiences, especially those who may not have a scientific background. Moreover, environments from millions of years ago are reconstructed with a mix of geological evidence and artistic sensitivity. Imagine a scene from the late Cretaceous period, a thriving landscape teeming with flora and fauna, colored and animated in ways that spark curiosity. Artists piece together the elements of these ancient worlds, balancing the need for scientific authenticity with the requirement that their work ignites interest and discussion among viewers. Ultimately, paleoartists serve as a bridge between the realms of science and art. Their work brings to life long-extinct creatures and allows the public to form a connection with a distant past. Through each brushstroke or digital rendering, they not only educate but also inspire wonder about the complexity and diversity of life on Earth. By combining scientific insights with imaginative concepts, they provide a portal into our planet's extraordinary history. North America was home to a remarkable variety of dinosaur species, each uniquely adapted to their environment. One of the most iconic was the Tyrannosaurus rex, a massive predator that roamed during the late Cretaceous period. With its powerful jaws and keen vision, the T-Rex stood out in North America's ecosystems as a top predator, contrasting sharply with smaller, more agile carnivorous dinosaurs found elsewhere, like the Velociraptor in Asia. Another notable species, the Triceratops, was a herbivore with a distinctive three-horned face and a bony frill. This dinosaur inhabited North America in the late Cretaceous and was quite different from the ceratopsians found in other regions, which often had different horn arrangements and sizes. The diversity among dinosaurs across continents can often be traced back to the unique environments they lived in, influencing their adaptations and behaviors. North American dinosaurs experienced a diverse range of climates, from lush forests to arid plains. This variety helped create unique ecosystems and fostered the evolution of dinosaurs like the hadrosaurids, known as duck-billed dinosaurs, which thrived with their specialized diets. On other continents, creatures like the sauropods, with their predominantly long necks and enormous size, adapted to different environments, showcasing how geographical and climatic factors shaped their evolution. Interestingly, as the continents drifted apart, unique dinosaur species emerged in isolation. For example, while North America was known for its fierce predators like the Allosaurus and the herbivorous giants such as Apatosaurus, Asia was home to many unique species as well, including the Therizinosaur, with its unusual body shape and feeding habits. This evolutionary story highlights the fascinating complexity of life on Earth millions of years ago, revealing how geography and environment played pivotal roles in shaping the diversity of these magnificent creatures. Recent discoveries of dinosaurs in Asia have significantly enriched our understanding of these fascinating creatures, revealing a more complex picture of their diversity and evolution. Fossils unearthed primarily from countries like Mongolia and China have uncovered evidence of bizarre and varied species that challenge previous assumptions. For instance, researchers have found feathered dinosaurs, suggesting that feathers may have evolved well before dinosaurs began to fly, indicating a deeper connection between these giant reptiles and the lineage that led to modern birds. One compelling example comes from the discovery of new theropods, a group that includes the famous Tyrannosaurus rex. In Asia, particularly in the Gobi Desert, fossils of small feathered theropods have emerged, demonstrating that this group was more diverse than once thought. The presence of these smaller, agile dinosaurs poses intriguing questions about their role in the ecosystem and how they might have interacted with their environment. This evidence implies that the evolutionary trajectory of theropods was not a straightforward path leading to birds, but rather a branching tree with many unique adaptations. Moreover, the excavation of large sauropods, long-necked dinosaurs, in China has illuminated the evolutionary dynamics of these gentle giants. Discoveries such as the newly identified species have provided insights into their morphology, feeding strategies, and growth patterns. The sheer variety found suggests that these titanic herbivores occupied different ecological niches, which adds layers to our understanding of how dinosaurs not only survived, but thrived in various habitats across what was once a vastly different Earth. Overall, the richness of dinosaur findings in Asia has prompted scientists to reassess their models of dinosaur evolution. These discoveries underscore the importance of this region in the narrative of dinosaur diversity and paleobiology, illustrating that the story of dinosaurs is ever evolving, much like the creatures themselves. Each new find opens a window into a complex past, enhancing our appreciation for these remarkable beings that roamed our planet millions of years ago. Paleontologists studying dinosaurs in Africa and South America encounter a variety of unique challenges, largely shaped by the region's diverse environments and geological histories. One of the primary hurdles is the remoteness of many fossil sites. Some of the most promising areas for dinosaur discovery are difficult to access, requiring long treks through rugged terrain, which can be physically demanding and time-consuming. These remote locations often have limited resources, making it hard for scientists to carry out prolonged research trips that might yield significant findings. Additionally, the climate can be a formidable barrier. Parts of Africa, for instance, face extreme conditions ranging from scorching heat to sudden rainstorms, which can hinder fieldwork and fossil preservation. In some cases, the seasonal rains can wash away potential fossils before they are discovered, while dry spells can crack and damage exposed remains. The climate in South America also presents challenges, particularly in regions like Patagonia, where extreme weather can delay excavation and enhance the risks to the delicate fossils buried in the sediment. Another factor is the complex stratigraphy of geological layers where fossils are found. In both continents, the geological formations can be intricate, making it difficult for paleontologists to date fossils accurately and understand the context of their discoveries. This complexity often requires extensive fieldwork and multiple studies to piece together the timeline of dinosaur existence and their environments. Each layer can tell a different story, but deciphering this narrative requires patience and perseverance. Lastly, the interaction with local communities and the legalities surrounding fossil excavations can pose challenges as well. Paleontologists must navigate cultural sensitivities, land ownership disputes, and legal restrictions regarding fossil collection. Building relationships with local groups can be essential for fostering collaboration and ensuring that research benefits not just the scientific community, but also the regions that host these incredible resources. Balancing scientific goals with respect for local culture and land rights is crucial in conducting responsible paleontological research. Australia, known for its unique wildlife and ecosystems today, once hosted a variety of dinosaurs that roamed its ancient landscapes. The diversity of Australian dinosaurs offers a compelling glimpse into the continent's distinct paleogeography, or ancient geography, and its climate history. During the Mesozoic era, when dinosaurs flourished, Australia was part of the supercontinent Gondwana, which significantly shaped its evolutionary trajectory. As Gondwana broke apart, Australia drifted northward, leading to its isolation. This separation resulted in unique evolutionary paths for the dinosaurs that inhabited the continent. For instance, the climate fluctuated from humid and lush environments in the north to drier, more arid conditions toward the south. These diverse ecosystems allowed for a range of dinosaur species to adapt and thrive, evolving distinct characteristics. From towering herbivores like the large sauropods to agile predators like the theropods, each species reflects the unique adaptations necessary for survival in their specific habitats. Fossil evidence indicates that, at various points in history, Australia experienced dramatic climate changes, contributing to the types of dinosaurs that lived there. During the warmer and wetter periods, forests flourished, supporting larger herbivorous species, while arid conditions led to adaptations favoring smaller, more efficient hunters. These shifts in environment directly influenced the biological diversity of the time, showcasing how climate and geography play crucial roles in shaping life on Earth. Moreover, Australia is home to some dinosaur fossils that give a clear indication of tropical and subtropical climates, suggesting rich ecosystems that supported a wide range of life forms. The continent's isolation not only fostered unique species of dinosaurs, but also made them vulnerable to extinction when significant changes occurred, such as the drastic shifts in climate at the end of the Cretaceous period. By examining the fossil record, we can gain valuable insights into how Australia's ancient landscapes and climates created a rich tapestry of life that continues to intrigue paleontologists and ignite curiosity about our planet's distant past. Dinosaurs roamed the Earth for over 160 million years, a significant span where they encountered dramatic climate changes. Fossil records reveal that these magnificent creatures experienced fluctuating temperatures, altered sea levels, and shifting ecosystems. For instance, during the Mesozoic era, when dinosaurs thrived, the climate was warmer, and in some regions, much wetter than today. Evidence suggests that these conditions led to the development of lush vegetation, which provided abundant food sources. As the planet underwent shifts, so did the dinosaurs. Fossilized remains show that some species migrated in response to climate changes, seeking more favorable habitats. For example, dinosaur fossils have been discovered in varied locations, indicating that as the climate warmed or cooled, they adapted by moving to areas where resources were more plentiful. The discovery of diverse plant and animal fossils in a range of climates helps illustrate how these creatures survived and evolved as their environments shifted over millions of years. Moreover, evidence from bone structure and sizes hints at adaptations. Some dinosaur species developed physical traits, such as changes in limb proportions or other features, that allowed them to better thrive in different climates. For instance, certain theropods evolved larger body sizes as a response to colder environments, which could help insulate against temperature fluctuations. In contrast, smaller species thrived in hotter conditions, where their size provided advantages in mobility and energy conservation. The evidence indicates that dinosaurs were not just passive victims of climate changes. Instead, they were dynamic beings capable of significant behavioral and physiological adaptations. The fossil record serves as a testament to their resilience and versatility, revealing a complex interplay between these ancient creatures and the ever-evolving planet they called home. This ability to adapt highlights the remarkable nature of dinosaurs, underscoring their legacy as one of the most successful groups of animals in the history of Earth. The study of dinosaurs and their adaptability to climate shifts presents a fascinating window into how life on Earth responds to changing conditions. Dinosaurs thrived for over 160 million years, witnessing significant fluctuations in climate, from scorching periods of high temperatures to ice ages that altered entire habitats. By analyzing their responses to these shifts, scientists can uncover patterns that may mirror our current environmental challenges. One key takeaway from the dinosaur era is that adaptability was crucial for survival. When faced with climate changes, some dinosaur species evolved new physical traits, diversified their diets, and adjusted their behaviors. For example, during warm periods, dinosaurs adapted to survive in lush, dense forests, while others thrived in arid, open environments. This illustrates a fundamental principle. Species that can adapt to rapidly changing conditions are more likely to endure. Understanding these adaptive strategies can inform modern conservation efforts as today's species face unprecedented rates of change. Additionally, studying the ecological impacts of climate shifts during the Mesozoic era can yield insights into contemporary ecosystems. Dinosaurs coexisted with a myriad of plants and other animals that evolved in response to their environmental challenges. Their interactions demonstrate the interconnectedness of life. Today, as we confront climate change, it is crucial to recognize how disruptions in one part of an ecosystem can have cascading effects throughout. Dinosaurs and their environment serve as a reminder that all species depend on a delicate balance. Finally, examining how dinosaurs responded to climate crises can guide our understanding of future challenges. For instance, the extinction events linked to dramatic climate changes underscore the fragility of ecosystems. By studying these past events, scientists can better predict the potential consequences of current climate issues, providing essential insights for policymaking and conservation. Ultimately, the lessons gleaned from dinosaurs remind us of the necessity of adaptability, resilience, and the urgent need to heed the environmental changes occurring today. The reign of the dinosaurs was marked by a vastly different atmosphere than what we experience today. Scientific studies suggest that during the Mesozoic era, the concentration of carbon dioxide was significantly higher, sometimes reaching levels up to 15 times greater than present-day amounts. This heightened level of carbon dioxide would have created a warmer and more humid environment, impacting not only the planet's climate, but also the physiology and metabolism of its inhabitants. With this increased warmth, dinosaurs likely developed unique adaptations to accommodate their metabolic needs. The higher temperatures could have facilitated more active lifestyles, encouraging a faster metabolism among these prehistoric giants. For instance, larger dinosaurs might have benefited from a metabolic system that accommodated their immense body size, allowing them to efficiently process the abundant plant material available in their lush, verdant surroundings. This could mean that some dinosaur species were warm-blooded, or at least exhibited characteristics of endothermy, which would have been critical in maintaining energy levels for hunting or foraging. Moreover, changes in atmospheric composition, particularly the increased oxygen levels, likely played a significant role in shaping the dinosaurs' physiology. Research indicates that oxygen levels during certain periods of the dinosaurs' existence were much higher than today, sometimes exceeding 20%. Such an environment would have supported more vigorous aerobic activity, allowing even the largest creatures to thrive. Enhanced oxygen supply could have contributed to greater body sizes and diverse physiological adaptations, promoting energy-efficient movements. As we examine the relationship between atmospheric conditions and dinosaur biology, it becomes evident that these ancient creatures were finely tuned to their environment. Changes in temperature and atmospheric composition were not just background factors, they were fundamental shapers of life. The physiological and metabolic adaptations that emerged in response to these conditions allowed dinosaurs to flourish across a variety of habitats, an enduring testament to their resilience and adaptability in a constantly changing world. Dinosaur discoveries have significantly enriched our understanding of Earth's prehistoric ecological history. Through the fossilized remains of these ancient creatures, we gather insights into ecosystems that existed millions of years ago. Each new find can paint a picture of biodiversity, climate conditions, and even the interactions between species. This journey through time is crafted from the evidence embedded in rocks, sediments, and fossils themselves, making paleontology a crucial window into Earth's distant past. For instance, the discovery of dinosaur fossils often includes not just the dinosaurs themselves, but the plants and other animals that coexisted with them. This reveals information about the kind of habitats that existed back then. In many cases, fossilized plants and pollen found alongside dinosaur bones provide clues to the climate, whether it was lush and humid or arid and dry. A well-preserved site can even show how ecosystems were structured, highlighting food chains that range from towering vegetation to predatory dinosaurs and smaller herbivores. Moreover, some discoveries have led to remarkable insights into the behavior and social structures of dinosaurs. Fossilized footprints, for example, can demonstrate whether dinosaurs traveled in herds or lived solitary lives. Such clues inform us not only about their daily activities, but also about the ecological roles they played within their environments. By understanding these roles, scientists can better piece together how dinosaurs adapted to and modified their ecosystems over time. As we continue to unearth new dinosaur fossils, the tapestry of Earth's ecological history grows richer. Each find prompts further questions, fueling ongoing research and debate among paleontologists. In this way, dinosaurs serve as key ambassadors of a past era, helping us fathom the rise and fall of ancient ecosystems and the dynamic processes that have shaped life on Earth through the ages. The extinction of the dinosaurs, a dramatic chapter in Earth's history, offers significant lessons for humanity as we face our own ecological challenges. About 66 million years ago, a catastrophic event, likely triggered by an asteroid impact, led to the extinction of approximately 75% of all species on Earth, including the iconic dinosaurs. This mass extinction is a stark reminder of how sudden environmental changes can drastically alter life on our planet. One crucial lesson is the interconnectedness of life. The disappearance of the dinosaurs paved the way for mammals to evolve and thrive. This demonstrates that ecosystems rely on a delicate balance. When one species is removed, it can create a ripple effect, leading to the decline or extinction of others. Today, as human activities deplete biodiversity through habitat destruction, pollution, and climate change, we risk destabilizing ecosystems that are vital for our planet's health and ultimately our survival. Another takeaway is the role of adaptability in survival. The species that survived the mass extinction were often those that could adapt to new environments and challenges. For instance, small mammals survived the harsh conditions that followed the asteroid impact. For humanity, this emphasizes the need for innovative solutions and adaptability in the face of ecological threats. Embracing sustainability, whether through renewable energy, conservation efforts, or responsible consumption, is crucial as we confront our rapidly changing environment. Finally, the extinction of the dinosaurs underscores the importance of foresight and precaution. Scientists believe that detecting and addressing early signs of environmental stress could have mitigated the impacts of past mass extinctions. For our species, paying attention to the warning signs of climate change, such as rising sea levels and increased weather extremes, is critical. By learning from the past, we have the opportunity to forge a more sustainable future, ensuring that humanity does not share the fate of the dinosaurs. Dinosaurs have captured the imagination of people for generations, yet many commonly held beliefs about these ancient creatures are not quite accurate. One prevalent misconception is that dinosaurs were all gigantic, towering beasts. In reality, dinosaurs exhibited a vast range of sizes. Some were as small as a chicken, while others, like the Argentinosaurus, truly were massive. The overemphasis on large species often leads to an incomplete understanding of the diversity within the dinosaur family. Another popular myth is the idea of dinosaurs as cold-blooded, lumbering creatures, akin to modern reptiles. Scientific evidence increasingly suggests that many dinosaurs were warm-blooded. This adaptive trait would have allowed them to be more active and energetic, enabling them to thrive in various environments. This portrayal of dinosaurs as sluggish and slow is misleading, as many species likely exhibited agility and speed. Furthermore, media often depicts dinosaurs living alongside humans, a concept made popular by movies and television shows. However, this is not grounded in reality. Dinosaurs became extinct approximately 65 million years ago, long before humans appeared on the scene. Our shared timeline may be enticing for storytelling, but it misrepresents the true chronology of life on Earth. Lastly, the classic image of dinosaurs covered in scaly skin is another misconception. In recent years, fossil evidence, including feathered dinosaurs, has illuminated the fact that many species were likely covered in feathers or proto-feathers, possibly for insulation, display, or even flight. This evolving understanding highlights the complexity of dinosaur biology and behavior, marking them as creatures far more dynamic than traditionally imagined. Scientific debates often arise in paleontology, particularly regarding the appearance and behavior of dinosaurs. One of the significant areas of contention has been their posture and skin texture. To resolve these debates, researchers utilize a combination of advanced technology and interdisciplinary studies, allowing them to gather more precise evidence than ever before. For instance, modern imaging techniques, such as computerized tomography and three-dimensional modeling, enable scientists to analyze fossilized remains more thoroughly. These methods reveal intricate details about the bone structure and possible musculature. By examining how the bones articulate, researchers can infer whether a dinosaur was more inclined to walk upright or adopt a more horizontal stance. Studies of related species, both extinct and living, can offer hints by drawing parallels in skeletal structure. In addition to technological advancements, scientists also deploy paleobiological studies. Trace fossils, footprints, and other geological context can provide insights into dinosaur behavior. Analysis of sediment layers and soil composition gives clues about their environment, which influences posture and movement. For skin texture discussions, fossil evidence of skin impressions, combined with the study of modern reptiles and birds, dinosaur descendants, can inform us about possible skin patterns and features. Moreover, the scientific community encourages communication and collaboration across disciplines, integrating insights from biology, physics, and even art in reconstructing these ancient creatures. Engaging in this kind of cross-pollination not only aids in resolving debates, but also enriches our understanding of dinosaur biology, creating a more nuanced picture of these incredible animals that once roamed our planet. Paleontology, the study of ancient life through fossils, has been shaped by several pioneering figures whose discoveries have transformed our understanding of dinosaurs. One of the most notable is Sir Richard Owen, who played a crucial role in defining the term dinosauria in the mid-19th century. Owen's identification of unique skeletal features common among these creatures laid the groundwork for the field. He named several species, including the iconic Megalosaurus, the first dinosaur to be scientifically described, which drew attention to these ancient reptiles' fascinating diversity and complexity. Another key figure is Edward Drinker Cope, known for his fierce rivalry with fellow paleontologist Othniel Charles Marsh, often referred to as the Great Bone Wars. Their competition led to the discovery and description of numerous dinosaur species in North America during the late 19th century. Cope's work included identifying the first nearly complete dinosaur skeleton in North America, the Hadrosaurus, which significantly advanced the study of dinosaurs and sparked public interest in these prehistoric giants. His extensive research has provided invaluable insights into dinosaur anatomy and evolution. Going further into the 20th century, we find Barnum Brown, who is famously credited with discovering the first partial skeleton of Tyrannosaurus rex in the year 1912. This groundbreaking find not only captured the public's imagination, but also reshaped our understanding of predatory dinosaurs. Brown's meticulous excavation techniques and his emphasis on fossil preservation have influenced how paleontologists approach fieldwork today, ensuring that future generations can study these monumental finds. Finally, the work of John H. Ostrom in the mid-20th century significantly shifted the perception of dinosaurs in the scientific community. Ostrom's research on the dinosaur Archaeopteryx helped establish the connection between dinosaurs and birds, indicating that many features we associate with birds, like feathers, were also present in some dinosaurs. This opened a new chapter in the study of evolution, highlighting the dynamic relationship between these ancient creatures and the modern species that we see today, truly capping off a narrative of scientific discovery that continues to evolve. Collaborative international research efforts have significantly deepened our understanding of dinosaur life, uniting experts from various countries and diverse disciplines. Fossil discoveries have emerged from regions around the globe, from the arid deserts of Mongolia to the lush landscapes of Argentina. By pooling resources, knowledge, and scientific expertise, researchers can piece together a more comprehensive picture of these ancient creatures and their environments. One remarkable aspect of international collaboration lies in the sharing of fossils and data across borders. A fossil found in one country can provide insights into a species that existed across multiple continents. For instance, the discovery of similar dinosaur bones in North America and Asia suggests that prehistoric ecosystems were interconnected in ways we are still uncovering. Access to a global database allows scientists to compare findings, leading to more robust conclusions about evolution, behavior, and ecology. Moreover, joint expeditions and research projects foster innovation and creativity in paleontology. International teams work together in the field, utilizing advanced technology such as imaging techniques and computer simulations to analyze fossils in unprecedented ways. This interdisciplinary approach combines geology, biology, and even art to reconstruct dinosaur habitats and behaviors, painting a vibrant portrait of life millions of years ago. Finally, international collaborations have also promoted the importance of education and outreach. Researchers share their findings not only with one another, but also with the public, sparking interest and fostering a new generation of scientists and enthusiasts. Educational initiatives, often born from these partnerships, provide communities with greater access to knowledge about dinosaurs, enhancing our collective appreciation for the intricate story of life on Earth. Through these collaborative efforts, we stand on the shoulders of giants, unlocking the secrets of the past with a united global effort. The evolution of dinosaurs, which spanned over 160 million years, provides fascinating insights that can enhance our understanding of early human development and evolutionary trajectories. One key lesson from the success of dinosaurs is their remarkable adaptability. Dinosaurs thrived in a variety of environments, showcasing an ability to survive and flourish under changing conditions. This adaptability emphasizes the importance of flexibility and resilience in the face of challenges, traits that are equally vital in the narrative of early human evolution. Additionally, the diversity among dinosaurs underscores a significant principle in evolution: specialization. Dinosaurs evolved into a wide range of forms and sizes, each adapted for specific ecological niches. This specialization allowed them to occupy various roles within their ecosystems, from gigantic herbivores to nimble carnivores. Parallel to dinosaurs, early humans showcased a proliferation of species and traits, each developed to solve particular problems in their environment, such as the development of tools, control of fire, and social structures. This diversity ultimately paved the path for Homo sapiens, teaching us about the advantages of adaptability and niche exploitation in evolutionary success. Another lesson lies in the impacts of extinction events. Dinosaurs faced catastrophic changes that led to mass extinctions, reminding us that adaptability to environmental shifts is crucial for survival. Early humans, too, faced various challenges, including climate changes, resource scarcity, and competition with other species. Understanding how species respond to drastic shifts can inform current studies on human resilience and adaptability in a world facing rapid changes due to climate and environmental issues. Lastly, studying dinosaur evolution illustrates the importance of cooperative behaviors. While the popular image of dinosaurs often leans towards solitary giants, many species likely lived in herds, illustrating social structures that enhance their survival. Early human evolution reflects similar themes, with social cooperation playing a critical role in our ancestors' ability to thrive. This focus on community highlights the shared benefits of collaboration, a lesson that resonates across both reptilian giants and early humans and continues to be relevant in our modern society as we work together to face global challenges. As we peer into the depths of Earth's distant past, we cannot help but marvel at the age of dinosaurs, a time that spanned from approximately 230 million years ago until about 66 million years ago. In the eyes of future human paleontologists, this era may appear as a vivid and complex tapestry woven with the lives of magnificent creatures that roamed our planet. They would approach this colossal chapter in Earth's history not just as a mere timeline, but as a rich ecological narrative filled with evolutionary milestones. To future researchers, the fossil record will provide crucial insights into the diversity of dinosaur life and the ecosystems they inhabited. Fossils form the backbone of paleontological studies, revealing not just the physical characteristics of these creatures, but also hints of their behaviors and interactions with the environment. These clues, from fossilized footprints to preserved nests, will help scientists reconstruct entire landscapes bustling with life. The footprints, for example, are not merely traces left behind. They are stories of movement, social behavior, and sometimes even of predation. In delivering an understanding of dinosaurs, future paleontologists will likely employ advanced technologies that we can only begin to imagine today. Techniques such as high-resolution imaging and genetic analysis of ancient remains may allow them to delve even deeper into the evolutionary tree. They might even uncover new species never before recognized, painting a broader and more intricate picture of life during the Mesozoic era. This can shift the way they view the age of dinosaurs, transforming it from an era dominated solely by giants to a time of biodiversity that included myriad small, agile creatures. Moreover, they will consider the climatic shifts and catastrophic events that punctuated this era, such as the asteroid impact that contributed to mass extinction. With their findings, these future scientists may reflect on the interconnectedness of life and the cycles of change on our planet. They could draw parallels to modern-day issues such as climate change and habitat destruction, exploring how past extinction events inform our understanding of the present. In this way, the age of dinosaurs will not just be a chapter in history, but a lens through which we examine our own existence and the fragility of life on Earth. The biodiversity of dinosaur species provides an intriguing glimpse into the complex ecosystems of the Mesozoic era, which spanned over 180 million years. Dinosaurs were not a monolithic group. Rather, they thrived in a variety of environments, adapting to the unique ecological niches available to them. This adaptability played a crucial role in their evolution, leading to the incredible diversity we recognize today. Different species occupied distinct habitats, from lush forests and open plains to arid deserts. For instance, some dinosaurs, like the long-necked sauropods, evolved to reach high into trees to dine on leaves, while others, such as the theropods, developed keen predatory skills to hunt smaller creatures. These adaptations were not just about survival, they were about the successful exploitation of the resources available in their environments. Each species had a role, whether as herbivores, carnivores, or omnivores, contributing to a balanced ecosystem. The presence of various dietary adaptations also points to the richness of the prehistoric food web. While larger species dominated certain niches, smaller dinosaurs filled in gaps, taking advantage of different food sources like insects, small plants, or even other small dinosaurs. This stratification allowed for a healthy competition for resources, which in turn fostered further diversity. Fossil evidence shows that as the environment changed, so did the types and numbers of dinosaurs, showcasing a dynamic relationship between species and their surroundings. Ultimately, the biodiversity seen in dinosaurs was a complex interplay of evolutionary processes, environmental pressures, and ecological roles. By studying the fossil record, scientists can reconstruct how these ancient creatures interacted with each other and their environments, offering a glimpse into a world where diversity was key to survival. This rich tapestry of life not only illustrates the dinosaurs' resilience, but contributes to our understanding of how biodiversity functions in nature, a lesson that remains relevant even today. Dinosaur biodiversity presents a captivating glimpse into the evolutionary experiments of life on Earth, just as modern species dynamics showcase ongoing adaptations and changes. Dinosaurs roamed the planet for over 160 million years, filling various ecological niches. During this extensive reign, they demonstrated incredible diversity, with thousands of unique species evolving to adapt to different environments, climates, and food sources. This diversification mirrors what we observe today, where species continually adapt to their surroundings, facing pressures from environmental shifts, competition, and even climate change. One significant parallel lies in the pattern of species radiations. Dinosaurs experienced several major diversification events, often triggered by significant ecological changes or mass extinctions. For instance, after the Permian-Triassic event, a devastating extinction that struck life on Earth, dinosaurs rapidly diversified, filling the void left by the fallen species. In our contemporary world, we also witness rapid diversification following extinctions or significant habitat alterations, though often these modern shifts are due to human impact or climate fluctuations rather than naturally occurring events. Another compelling connection between the past and present is the relationship between climate and diversity. During the Mesozoic era, climate played a pivotal role in shaping ecosystems. Fluctuations in temperature and atmospheric conditions influenced the distribution of both dinosaurs and the plants they relied on. Today, climate change similarly acts as a driving force, reshaping habitats and affecting species survival, pushing some towards extinction while creating opportunities for others to thrive. Finally, the concept of human-induced extinction provides a stark contrast between now and the time of dinosaurs. While massive extinctions on Earth reshaped the course of evolution, the recent loss of species due to human activity serves as a cautionary tale. Just as the end of the age of dinosaurs opened up a myriad of opportunities for mammals, we are witnessing a pivotal moment of change, where our actions shape the fate of countless species. The ongoing dynamics of biodiversity can teach us about resilience, adaptation, and the interconnectedness of all life on our planet. Dinosaurs, those majestic creatures that roamed the Earth millions of years ago, have left an indelible mark on contemporary science and technology, particularly through the principles of biomimicry and robotics. As researchers study the physical structures and movements of these ancient animals, they often find inspiration that leads to innovative designs and solutions in modern engineering. For instance, the way dinosaurs moved and adapted to their environments offers valuable insights into creating more efficient machines and structures. One of the most compelling examples of this influence is in the field of robotics. Engineers have closely examined the locomotion of dinosaurs to design robots that mimic their movements. By analyzing the biomechanics of dinosaurs like the Tyrannosaurus rex or the Velociraptor, researchers are developing robotic systems that can efficiently navigate uneven terrains or perform specialized tasks. These advancements not only improve robotic mobility, but also often lead to a broader understanding of movement dynamics that can be applied in various areas, from healthcare to manufacturing. Biomimicry, which seeks solutions inspired by nature, has embraced the unique features of dinosaurs as well. For instance, scientists have studied the structure of dinosaur bones for insights into creating stronger, lighter materials. The hollow yet sturdy design of certain dinosaur bones can guide the development of new construction materials that are both resilient and lightweight, helping to reduce energy consumption in buildings and infrastructure. Furthermore, the study of feathers, particularly in theropod dinosaurs, has influenced advancements in aerodynamics. Their unique design offers lessons in reducing drag and enhancing efficiency, which can be applied in aerospace engineering. This fascinating cross-pollination between ancient life forms and modern technology continues to unfold, reminding us that the echoes of these magnificent creatures still resonate in today's innovations, bridging the gap between past and present. Dinosaur-themed museums and exhibits serve as vibrant gateways to our planet's distant past, playing a vital role in preserving natural history. These institutions curate and display remarkable fossil collections, many of which consist of skeletal remains and casts of dinosaurs that roamed the Earth millions of years ago. By meticulously maintaining these artifacts, they provide an invaluable record of life before humans, allowing us to glimpse an era defined by colossal creatures. But these museums do more than simply showcase fossils. They engage in research, contributing to our understanding of paleontology, the the study of ancient life. This research helps uncover the behaviors, habitats, and extinction events of dinosaurs, providing a deeper context for the evolutionary story of life on Earth. By sharing these findings with the public through exhibits, lectures, and educational programs, these institutions illuminate the scientific process and foster a love of discovery in their visitors. Moreover, dinosaur exhibits inspire awe and curiosity in people of all ages. For children in particular, these fascinating displays can ignite a passion for science and natural history. Interactive exhibits, engaging visuals, and hands-on learning experiences help to make complex scientific concepts more accessible and enjoyable. This educational outreach is essential for nurturing future generations of scientists, conservationists, and informed citizens who appreciate the importance of our planet's history. Finally, these museums often collaborate with schools and community organizations to amplify their educational efforts. They become vital community hubs that promote curiosity and discussion about Earth's evolving landscape. By creating a space where ancient history connects with modern-day environmental issues, they instill a sense of responsibility in visitors to protect our planet and safeguard the legacy of life that has come before us. Ultimately, dinosaur-themed museums and exhibits play a crucial role in bridging the past with the present, inspiring future generations to explore and cherish the wonders of our world. The study of dinosaurs, often revered as giants of the past, holds a dual role in both scientific inquiry and the world of imaginative exploration. On one hand, paleontologists meticulously examine fossilized remains, uncovering details about the anatomy, behavior, and ecosystems that existed millions of years ago. This scientific curiosity drives a deeper understanding of evolution, climate change, and the intricate web of life that has existed on our planet. Each new discovery, whether it is a bone, track, or even traces of ancient nests, offers clues that help scientists construct a more accurate picture of our Earth's history. Conversely, the allure of dinosaurs extends beyond academia into the realm of imagination and culture. These colossal creatures have sparked the creative minds of artists, writers, and filmmakers alike. From the classic tales of The Land Before Time to the groundbreaking visual effects in Jurassic Park, dinosaurs prompt us to visualize worlds that are both foreign and fascinating. This imaginative exploration allows people of all ages to engage with science in a way that feels dynamic and storytelling-driven, enticing a broader audience to consider the importance of Earth's natural history and its relevance to contemporary challenges. Moreover, the fascination with dinosaurs encourages public interest in science and education. Museums worldwide feature engaging displays and hands-on exhibits, drawing families to learn more about these ancient reptiles. Interactive experiences allow visitors to delve into paleontology's rigorous methods while also stoking their imaginations. The blend of fact and fantasy captivates young minds, inspiring future generations to pursue careers in science and to continue the quest for knowledge about our world and its past. The ongoing study of dinosaurs serves as a bridge between factual discovery and creative expression. It fosters a unique synergy between rigorous scientific inquiry and the boundless realm of imagination, reminding us that the story of life on Earth is not just a history lesson, but a narrative full of wonder and possibility. Together, these elements inspire a holistic appreciation for the past and our place within the ever-evolving tapestry of life. The idea of resurrecting dinosaurs, often referred to as de-extinction, has captured the public imagination, especially with the success of films featuring these magnificent creatures. Scientifically, the concept is theoretically rooted in the possibility of using genetic technology, such as cloning and gene editing, to recreate extinct species. However, the practicality of this process, particularly for creatures as ancient as dinosaurs, presents monumental challenges. DNA degrades over time, and the oldest dinosaur DNA scientists have recovered is around 1 million years old, while most dinosaurs went extinct over 65 million years ago. This immense gap makes the extraction of usable DNA extremely unlikely. Current scientific efforts to understand the genetics of related species, such as birds and reptiles, provide a potential pathway for gene editing. By studying their genomes, researchers hope to identify specific traits that could allow them to engineer a modern-day descendant with dinosaur-like characteristics. Projects involving the closely related chicken, for instance, have already begun to explore this avenue. Scientists envision manipulating genetic pathways to reproduce features that might resemble those of their ancient relatives. However, the pursuit of such extraordinary projects raises profound ethical questions. One of the primary concerns is the ecological impact of introducing a dinosaur species into today's world, particularly since ecosystems have evolved dramatically since their extinction. Would these creatures disrupt existing habitats, or could they serve as a vital part of a conservation effort? The implications extend beyond just ecological concerns. There are also moral considerations regarding the welfare of de-extinct organisms. How do we ensure the well-being of an animal brought back to life when its original environment no longer exists? Furthermore, the resources involved in attempting such complex genetic work could divest attention and funding from current conservation efforts. As many species today face extinction due to human activities, the focus on resurrecting dinosaurs could overshadow the pressing needs for protecting existing wildlife. While the science of genetic technology may inch closer to making the unimaginable plausible, the ethical dilemmas it presents are intricate and demand careful contemplation. The fascination with bringing dinosaurs back is not just about recreating history. It's about understanding our responsibilities toward life on Earth now and in the future. Recent advances in DNA extraction and analysis have opened exciting new avenues in our understanding of dinosaur genetics. For many years, scientists believed that the organic materials found in dinosaur fossils were too degraded to recover DNA. However, technological improvements have allowed researchers to cleverly extract fragments of ancient genetic material from well-preserved specimens, primarily those encased in amber or other fossilized materials. This breakthrough means that we can now probe deeper into the biological aspects of dinosaurs than previously thought possible. One of the most remarkable revelations from these studies is the genetic relationships between dinosaurs and modern birds. Genetic analysis has provided persuasive evidence that birds are indeed modern-day descendants of theropod dinosaurs. This discovery has enriched our understanding of evolutionary biology and underscores the idea that the lineage of dinosaurs is not entirely extinct, but rather lives on in avian form. The ability to study their genes helps us make connections between the behaviors, physical attributes, and even some aspects of their appearance. Moreover, researchers have begun to examine the potential for identifying specific traits that may have existed in dinosaurs. By comparing dinosaur DNA fragments with the genetic codes of contemporary species, scientists can infer characteristics such as coloration, size, and even metabolic processes. Such analyses provide fascinating insights, not just into dinosaur biology, but also into how they may have responded to their environments and adapted over millions of years. Another intriguing aspect of this research is the ongoing quest to unlock the fossilized genome of major dinosaur groups. While full genome sequences remain elusive, the partial sequences achieved through modern techniques promise to refine our understanding of how these magnificent creatures lived and interacted with their ecosystems. As we continue to explore these genetic mysteries, the stories of dinosaurs grow richer, revealing a dynamic web of life that has persisted in various forms for over 100 million years. Virtual reality, often abbreviated as VR, has become an exciting tool in modern education. It creates immersive experiences that transport users back in time, particularly to eras inhabited by dinosaurs. Through VR technology, students can step into lifelike environments where they can interact with dinosaurs and experience their habitats in a way that traditional education methods simply cannot replicate. Imagine donning a VR headset and finding yourself surrounded by a lush prehistoric landscape. The sounds of a bustling ecosystem fill the air, and you can see towering dinosaurs like the majestic Brachiosaurus grazing on treetops. This vivid realism allows learners to engage with their subjects actively, making the information more memorable. When students can visualize and even move through these ancient worlds, it deepens their understanding of both dinosaur behavior and the ecosystems of the time. Moreover, VR can simulate various scenarios. Students might experience the day-to-day life of a dinosaur or witness powerful natural events like volcanic eruptions or asteroid impacts that shape the planet's history. These simulations provide context that helps learners grasp not just who the dinosaurs were, but also how they lived, what they ate, and why they became extinct. Such experiences foster curiosity and encourage questions about evolution, geology, and paleontology. In addition, educational institutions are beginning to integrate VR lessons into their curricula. Teachers can guide students through these experiences, encouraging discussion and reflection. This innovation not only enhances engagement, but also supports diverse learning styles. By offering a fresh perspective on history and science, virtual reality is redefining how we learn about our planet's distant past, sparking a deeper appreciation for the complexity of life on Earth. Interactive simulations and games have significantly transformed the way the public engages with the fascinating world of dinosaurs. Unlike traditional forms of learning, these digital experiences immerse players in richly detailed environments where they can explore prehistoric landscapes, interact with various species, and even participate in simulated paleontological digs. This hands-on approach makes learning about dinosaurs more engaging and memorable, as players not only absorb facts but also experience the thrill of discovery in a dynamic setting. These simulations and games often incorporate accurate scientific information from paleontology, which enhances the educational value while entertaining players. For instance, as individuals create their own dinosaur-themed parks or uncover fossils, they learn about different species, their habitats, and the conditions that led to their extinction. This blend of education and entertainment makes complex concepts more accessible, appealing to a wide audience from children to adults who may not have previously shown an interest in paleontology. Furthermore, interactive experiences facilitate community engagement through online platforms and social media. Players can share their discoveries, discuss strategies, and even collaborate on in-game challenges, creating a sense of camaraderie among dinosaur enthusiasts. This not only spreads knowledge, but also fosters a sense of community, encouraging more people to delve into the rich history of these magnificent creatures. The influence of gameplay extends beyond the screen, often sparking curiosity that leads to further exploration of documentaries, books, and educational programs about dinosaurs. Interactive simulations and games serve as a bridge connecting science and entertainment. They capture the imagination of users, making complex scientific ideas about dinosaurs not only understandable, but also exciting. By tapping into our natural curiosity and desire for exploration, these digital tools have played a vital role in enhancing public interest and knowledge of our distant prehistoric past. Artistic interpretations of dinosaurs have undergone a remarkable transformation over the years, reflecting not only advancements in paleontological understanding, but also changes in cultural perspectives. Early drawings, often created in the 19th century, presented dinosaurs as lumbering reptilian beasts, frequently depicted in battle or as part of fantastical scenes. These illustrations were heavily influenced by the limited fossil evidence available at the time, leading to a portrayal of dinosaurs that often leaned towards the dramatic and sensational. As paleontology progressed and more fossil discoveries were made, artists began to adapt their interpretations. Techniques such as studying bone structure, fossilized footprints, and even modern bird anatomy allowed artists to envision dinosaurs in a more scientifically accurate light. For instance, the popular depiction of dinosaurs as feathered creatures emerged as evidence pointed towards the close evolutionary relationship between birds and some dinosaur species. Such insights allowed for more dynamic representations that captured the agility and complexity of these ancient animals. In the contemporary art world, dinosaurs have found a versatile place, moving beyond traditional sculpture and painting into multimedia installations and interactive exhibits. Artists now explore themes of extinction, evolution, and humanity's relationship with nature. Sculptors may create hyper-realistic, life-sized models that invite viewers to engage with these creatures in new ways, fostering a deeper connection to Earth's biological history. On the other hand, installations may use technology to animate dinosaurs in a virtual space, blending art and science to capture imaginations. This evolution of artistic representation has not only elevated public interest in dinosaurs, but has also served as a platform for education. These modern artworks challenge audiences to consider the fleeting nature of existence and the lessons we can learn from life forms that dominated the Earth millions of years ago. Through art, we are reminded that our understanding of the past is ever growing, just as our imaginations continue to reshape it. Public installations and art pieces featuring dinosaurs serve as powerful tools for cultural and historical storytelling. These striking exhibits often evoke a sense of wonder and curiosity, reminding us of a time long before human civilization. By showcasing these magnificent creatures, art installations can spark discussions about evolution, extinction, and the history of life on Earth. They bridge the gap between scientific understanding and public interest, making complex ideas accessible to all ages. Beyond education, dinosaur-themed installations foster community engagement and inspire creativity. They act as focal points in parks, museums, and urban spaces, inviting people to explore and interact with art in dynamic ways. When individuals encounter a life-sized dinosaur sculpture or mural, it can transport them to a world where these giants roamed freely, igniting their imaginations and encouraging them to ponder their place in the natural world. These artistic representations also carry a cultural significance, often reflecting regional histories or local paleontological discoveries. They celebrate humanity's fascination with these creatures and echo our collective story of exploration and understanding. For many communities, dinosaur exhibits can become a source of pride, showcasing the area's unique contributions to science and culture while attracting tourists eager to engage with these prehistoric narratives. Lastly, dinosaurs serve as a universal symbol connecting us to our distant past. As we admire the artistry and craftsmanship involved in these installations, we also reflect on our planet's history and the ongoing journey of life. In this way, art featuring dinosaurs not only tells the story of ancient times, but also emphasizes the importance of stewardship for the Earth, reminding us to protect the wonders that still exist today. The planet's surface is a tapestry of movement shaped by the slow yet powerful forces of tectonic plates. Over millions of years, these plates have shifted, colliding and drifting apart, crafting continents and oceans. This geological activity created varied habitats from lush forests to arid deserts, profoundly influencing where dinosaurs could live and thrive. As continents shifted, the climate and environment of these regions transformed, leading to a dynamic landscape that fostered both competition and adaptation among the dinosaurs. Volcanic eruptions played a pivotal role as well, adding another layer of complexity to the prehistoric world. When volcanoes erupted, they released ash and gases into the atmosphere, altering temperatures and affecting the environments that surrounded them. For example, a significant eruption could lead to a cooling period, dramatically changing the habitat for countless species. Similarly, volcanic islands provided isolated environments where unique species could evolve due to limited interaction with mainland dinosaurs. This isolation often resulted in the development of specialized features suited for these distinct habitats. As these habitats changed, so too did the evolutionary paths of the dinosaurs. Species adapted to new climates and food sources, leading to an astonishing diversity. Some dinosaurs became suited for vast, open plains, while others developed traits necessary for survival in dense forests or swamps. Through this process of adaptation, natural selection favored those that could best navigate their shifting environments, leading to the rise and fall of various dinosaur species over the ages. Ultimately, the interplay between tectonic movements and volcanic events sculpted the Earth, creating a dynamic backdrop for the story of the dinosaurs. These geological forces not only crafted their world, but also acted as a catalyst for evolution, driving the incredible diversity and adaptability of these magnificent creatures. In understanding this connection, we can appreciate how the very ground beneath our feet has a profound influence on the life that has flourished above it. Sedimentary layers and rock formations are like pages in a book, each telling a unique story about Earth's history and the life forms that inhabited it. These layers, formed over millions of years through processes such as erosion, deposition, and compaction, contain fossils and clues about the environment in which these creatures lived. By studying these layers, paleontologists can piece together the habitats of dinosaurs and the ecosystems that existed alongside them. Each sedimentary layer often corresponds to a specific period in geological time. The composition of these layers can reveal details such as whether an area was once a lush forest, a sandy desert, or an underwater seabed. For example, sandstone may indicate a former beach environment, while limestone suggests the area was once submerged in ocean water. Fossils found within these layers, including bones, teeth, and footprints, provide critical insight into the kinds of dinosaurs that roamed the Earth, their behaviors, and their interactions with the environment. Furthermore, the arrangement of these rock layers can elucidate historical climatic changes. Variations in sediment color and type often indicate shifts in climate and vegetation, helping scientists understand how ancient ecosystems responded to these changes. By using techniques such as radiometric dating, researchers can also determine when specific dinosaurs lived, allowing a timeline to be established that connects them to the plants they grazed on and the environmental challenges they faced. Ultimately, the study of sedimentary layers and rock formations is essential in reconstructing the ancient world. They not only give us a glimpse into the lives of dinosaurs, but also enhance our understanding of biodiversity, extinction events, and the dynamic nature of our planet's climate through geological time. Each layer is a testament to life's resilience and adaptability, revealing secrets that continue to captivate scientists and enthusiasts alike. Reconstructing the habitats of ancient dinosaurs offers fascinating insights into the ecosystems they thrived in. One major tool used in this task is palynology, the study of pollen and spores found in sediment layers. By examining these microscopic plant remains, scientists can piece together the types of vegetation that existed at various points in history. For instance, the presence of certain pollen types can indicate whether an area was dominated by coniferous forests, flowering plants, or even grasslands during the age of dinosaurs. Alongside palynology, geochemical proxies play a crucial role in habitat reconstruction. Researchers analyze the chemical composition of sediments, including elements like carbon and oxygen isotopes. These elements provide clues about ancient climate conditions, such as temperature and humidity, which in turn influence what types of plants could grow in a region. For example, higher levels of certain isotopes might suggest a warmer and wetter climate, conducive to lush, dense forests, while lower levels could indicate drier, more arid conditions. Combining evidence from palynology and geochemical analyses allows scientists to create a more comprehensive picture of dinosaur habitats. This multidisciplinary approach reveals not only the vegetation types, but also the climate-related factors that shape these environments. The results unveil dynamic landscapes, showing how prehistoric ecosystems changed over time due to shifts in climate or the movements of tectonic plates. This research does more than just inform us about the past. It helps us understand how ecosystems evolve and respond to changes, drawing connections between ancient climates and today's environmental concerns. By delving into these scientific methods, we enhance our appreciation of the complex world dinosaurs inhabited millions of years ago, illuminating the intricate relationships between dinosaurs, their environments, and the ever-changing planet we live on. During the Mesozoic era, which spanned from approximately 253 million to 65 million years ago, the Earth experienced significant fluctuations in sea levels. These changes had a profound impact on the environment, creating dynamic landscapes that influenced the migration and evolution of dinosaurs. As sea levels rose and fell, entire ecosystems transformed, leading to the isolation or connection of land masses. When sea levels surged, vast regions were flooded, creating inland seas that divided continents. This led to the emergence of new habitats, allowing some dinosaur species to thrive and diversify in response to altered environments. Conversely, during periods of lower sea levels, land bridges formed, enabling species to migrate across previously disconnected regions. This movement could lead to the mixing of different dinosaur populations, promoting genetic diversity and the emergence of new species. Interestingly, these fluctuations also influenced food sources and climate conditions. Rising waters often created wetland environments rich in vegetation, which could support herbivorous dinosaurs. As their food sources flourished, predator species would also benefit, creating a complex web of relationships that shaped evolutionary pathways. Additionally, the climatic variations associated with sea level changes, such as temperature shifts and humidity levels, further pressured species to adapt, driving evolution. Ultimately, the interplay of rising and falling sea levels during the Mesozoic was more than just a backdrop. It served as a catalyst for change. The migration patterns shaped by these fluctuations contributed to the rich tapestry of dinosaur life, with each shift in the environment leaving its mark on the evolution of these incredible creatures. This era reminds us that the forces of nature are ever present, dynamically shaping the course of life on Earth. The study of dinosaur brains and their neurological structures offers a fascinating insight into the cognitive abilities of these ancient creatures. Contrary to what one might assume, dinosaurs did not simply rely on brute strength. They possessed a variety of mental capacities. By examining the fossilized remains of dinosaur skulls, scientists can infer the size and complexity of their brains, which can reveal clues about their sensory perceptions, behaviors, and even social dynamics. For instance, comparing the size of a dinosaur's brain to its body, known as the encephalization quotient, can indicate how intelligent it might have been. Tyrannosaurus rex, often viewed solely as a savage predator, actually had a relatively large brain for its body size. This suggests that it may have possessed advanced sensory capabilities and possibly even complex behaviors. Additionally, the structure of its brain indicates a keen sense of smell, which would have been crucial for hunting and foraging. Moreover, the study of specific regions of dinosaur brains can unveil a wealth of information. For example, some dinosaurs appear to have had well-developed optical lobes, indicating a reliance on vision that may have been vital for detecting movement and navigating through their environments. Other areas associated with memory and learning show that some species may have had more sophisticated social structures, potentially traveling in packs or exhibiting complex mating behaviors. Ultimately, by piecing together the physical evidence from their fossilized remains, scientists are beginning to build a clearer picture of how dinosaurs interacted with their world. Each find contributes to our understanding of their cognitive abilities, and as technology progresses, techniques like advanced imaging might further illuminate the neurological complexities of these incredible animals that roamed our planet millions of years ago. The intelligence of certain dinosaur species has long fascinated scientists and enthusiasts alike, largely due to the close evolutionary relationship between dinosaurs and modern birds. Studies of the brain structure and body size ratios in various dinosaur fossils suggest that some of these ancient creatures might have had cognitive abilities surpassing those of today's reptiles. For instance, theropods, the group of dinosaurs that includes the infamous Tyrannosaurus rex and the agile velociraptor, had relatively large brains for their body size. This feature hints at the potential for complex behaviors that could rival or even surpass some of our current reptilian inhabitants. In comparison, modern birds are considered the most intelligent among today's avian and reptilian species. Birds such as crows, parrots, and ravens demonstrate problem-solving skills, tool use, and intricate social behaviors. This advanced cognitive capacity is partly attributed to their brain structure, which includes a high number of neurons concentrated in areas associated with intelligence. The similarity in the brain architecture between these birds and certain theropod dinosaurs suggests a common link in cognitive evolution, where both groups may have developed sophisticated behaviors in response to similar environmental challenges. Interestingly, the link between intelligence and social behavior is evident in both modern birds and some dinosaur species. Fossil evidence indicates that certain dinosaurs may have exhibited social dynamics, such as hunting in packs or nesting in colonies, which can lead to social learning and the development of more complex behaviors. These parallels illustrate that while dinosaurs are often rendered as simple creatures of the past, there was a diversity of intelligence and behaviors that could rival those found in today's birds. Ultimately, as we delve deeper into our understanding of dinosaur biology and their relationships with modern species, it becomes increasingly clear that intelligence within these ancient animals was more nuanced than previously thought. This ongoing research opens up new avenues of inquiry, allowing us to better appreciate the richness of life that once roamed our planet and its connection to the avian world we know today. The ancient world of dinosaurs was not solely defined by their dominance. It was also characterized by complex relationships with other species. One of the most fascinating aspects of these interactions is the evidence of symbiotic relationships, where different species lived in close partnership, providing mutual benefits. An iconic example comes from the plant-eating dinosaurs, which often supported various ecosystems by promoting the growth of the flora they fed on. As these large herbivores grazed, they not only consumed vast quantities of vegetation, but also dropped seeds across the landscape in their droppings, aiding in plant dispersal and diversity. Another area of exploration is the evidence from coprolites, which are fossilized dinosaur dung. These remnants can reveal dietary habits and interactions with other organisms. For instance, some coprolites have contained fragments of bones from small mammals or reptiles, suggesting predation or scavenging. This indicates that smaller species might have lived in the shadow of larger dinosaurs, either competing for resources or thriving off the leftovers of their meals. Such interactions point to a web of life where each creature played a role in the broader ecosystem. Moreover, studies of fossilized footprints have shown patterns of behavior that suggest social interactions among dinosaurs. Some species, such as theropods, have been found in tracks that indicate communal nesting habits. This implies that there was some form of protection and nurturing, showcasing a social symbiosis. Dinosaurs may have flocked together not just for safety in numbers, but also to raise their young in groups, further enhancing their chances of survival against predators. In some cases, we even see evidence of large predatory dinosaurs collaborating with smaller species. Fossils from certain locations show that smaller creatures like prehistoric birds often roamed alongside larger theropods. This could suggest a symbiotic relationship based on mutual alertness. While larger dinosaurs provided protection through their sheer size, smaller species might have offered insight into danger through their precise vision and quick movement. These intricate relationships reflect the dynamic and interconnected nature of life during the age of dinosaurs, providing glimpses into a world both wild and cooperative. Phylogenetic studies and cladistic analysis are vital tools in understanding the complex web of relationships among dinosaurs and their evolutionary branches. By examining the shared characteristics among various species, scientists can reconstruct the family trees of dinosaurs, illustrating how diverse groups are related through common ancestry. This approach allows for a clearer picture of how different species evolved over millions of years, based on both physical traits and genetic data. Cladistics, in particular, utilizes branching diagrams called cladograms. These diagrams map out evolutionary relationships by grouping organisms based on shared derived characteristics. For instance, if two species share a particular feature that is absent in more distant relatives, It suggests they have a common ancestor who also possessed that trait. This method emphasizes lineage and helps paleontologists understand the sequence of evolutionary changes that occurred. Phylogenetic studies often incorporate fossil evidence alongside modern genetic techniques, creating a comprehensive view of how dinosaurs might have adapted to their environments throughout the Mesozoic era. By analyzing the fossil record for anatomical features, researchers can date when certain characteristics emerged or disappeared, further refining our understanding of the timeline of dinosaur evolution. Additionally, these studies help clarify previously ambiguous relationships among species. They can reveal surprising links, such as identifying close relatives among previously categorized distant families. As a result, by piecing together the evolutionary puzzle, phylogenetic studies and cladistic analysis not only enhance our knowledge of dinosaurs, but also provide insights into the broader patterns of life on Earth and how it has evolved over time. Comparative anatomy and DNA analysis are two vital tools that have greatly enriched our understanding of dinosaur lineage and development. Comparative anatomy involves studying the physical structures of different species, revealing how traits are related across the tree of life. For instance, by examining the bone structures of modern birds, reptiles, and other animals, scientists can infer evolutionary connections to dinosaurs. Features like the arrangement of limbs, skull shape, and even feather development offer clues about how these magnificent creatures lived and evolved over millions of years. The fossil record plays a crucial role in this aspect. By comparing fossils of dinosaurs with those of their closest living relatives, paleontologists can map out physical changes over time. This process also acknowledges that some species, once thought extinct, may have living descendants today. A prime example lies in the relationship between birds and theropod dinosaurs, where similarities in skeletal structure have led to the understanding that modern birds are, in fact, avian dinosaurs. DNA analysis, on the other hand, has taken this investigation a step further. Although the preservation of dinosaur DNA is incredibly rare, researchers have found ways to extract genetic material from more recent fossils, including those of mammals and birds. This genetic data can reveal insights into the evolution of various traits and characteristics, helping scientists determine how certain features may have developed in dinosaurs. By comparing the genetic markers of different species, researchers begin to piece together the intricate puzzle of evolutionary history. Together, these methods paint a broader picture of how dinosaurs adapted to their environments and how they relate to the organisms that exist today. The integration of comparative anatomy and DNA analysis not only enhances our understanding of the specific lineage of dinosaurs, but also showcases the connectedness of all life on Earth. This exploration of ancestry and adaptation fuels our curiosity, providing a deeper appreciation of the natural world and its historical tapestry. During the age of dinosaurs, these magnificent creatures faced various predators that posed a significant threat to their survival. Some common predators included large theropods like Tyrannosaurus rex and Velociraptor, which were equipped with sharp teeth and claws designed for hunting. Additionally, smaller carnivorous dinosaurs, such as Calophysis, were agile hunters that might target young or weaker dinosaurs. This predator-prey dynamic played a crucial role in shaping the behavior and evolution of dinosaurs over millions of years. Dinosaurs developed a range of defensive strategies to counter these predators. Many of the larger herbivorous dinosaurs, like Triceratops and Stegosaurus, grew formidable physical features as a means of protection. For example, Triceratops had 3 distinct facial horns and a bony frill that acted as both armor and a deterrent against attackers. Similarly, the plated back of Stegosaurus could serve as a shield, while its sharp tail spikes could be used as a weapon. In addition to physical adaptations, many dinosaurs relied on behavioral strategies to avoid predation. Herding behavior was common among certain species, creating safety in numbers. This social behavior helped spot predators early, allowing the group to flee or defend itself more effectively. Some dinosaurs may have taken advantage of their surroundings, using dense vegetation or rocky terrain to hide from lurking threats. Lastly, speed and agility were also critical factors in survival. Smaller dinosaurs could dart away quickly from larger predators, while even some of the larger species could reach impressive speeds to escape danger. This complex interplay of physical adaptations and behavior highlights the evolutionary arms race that existed between predators and prey during the age of dinosaurs, revealing an intricate web of life that underscored the balance of their ecosystem. During the age of dinosaurs, a rich tapestry of life flourished, filled with an array of species vying for supremacy. Interspecies competition was frequent and varied, driven by the dynamic interactions among dinosaurs and other megafauna, including marine reptiles and flying reptiles. For example, large herbivorous dinosaurs, such as the long-necked sauropods, consumed vast quantities of vegetation, leading to competition with smaller herbivores that shared their habitats. This competition often dictated the dietary adaptations of these species, as they developed unique feeding strategies to minimize overlap in their food sources. Predators had their struggles too. Theropods, the group that included the formidable Tyrannosaurus rex, faced competition from other carnivorous dinosaurs, such as the agile velociraptor and the massive Allosaurus. Each carnivore adapted distinct hunting methods and physical traits to secure its place atop the food chain. Such competition shaped their evolution, leading to variations in size, speed, and social behaviors. It is fascinating to consider how these adaptations resulted from the intense pressure of survival, reinforcing the idea that the natural world is a complex web of interdependence and competition. Beyond land-dwelling creatures, competition extended to the skies and the oceans. Pterosaurs, often misunderstood as mere flying reptiles, were actually highly specialized and dominated the aerial niches. They competed with other flying animals for food sources, like fish and small dinosaurs. Similarly, marine reptiles, such as ichthyosaurs and plesiosaurs, occupied the oceans, competing for similar prey. Their evolutionary adaptations, including streamlined bodies and impressive swimming abilities, exemplify the fierce competition for survival in varying environments. These interactions illustrate a vibrant ecosystem where the rules of competition were ever present. As species adapted to overcome their rivals, the landscape of life continually transformed. The study of these ancient relationships reveals not only the dynamics of competition, but also a deeper understanding of how these remarkable creatures evolved to navigate their world's challenges. The legacy of this competition among dinosaurs and megafauna helps us appreciate the intricate balance of life that stretches back millions of years. Throughout history, paleontologists have uncovered remarkable sites that offer window views into the age of dinosaurs. One of the most significant is the Hell Creek Formation in Montana, USA. This site is renowned for its well-preserved fossils, including those of the mighty Tyrannosaurus rex and the armored Triceratops. The rich sediment layers provide a snapshot of the late Cretaceous period, around 66 million years ago, just before the mass extinction event that wiped out many dinosaur species. Each discovery here enhances our understanding of dinosaur behavior, ecology, and the environments they inhabited. Another critical site is the Liaoning province in northeastern China. This region is famed for its exquisite fossil beds, which have revealed a treasure trove of feathered dinosaurs, bridging the gap between dinosaurs and modern birds. The fossils here date back to the early Cretaceous period, around 130 million years ago, and include remarkable specimens like Sinosauropteryx. These discoveries have provided essential insights into the origins of flight, as well as the evolutionary adaptations that led to the birds we see today. In Argentina, the Patagonia region hosts the fossil-rich area known as the Ischigualasto Formation. This site is notable for its contributions to understanding the earliest dinosaurs, dating back to the late Triassic period, approximately 240 million years ago. Fossils unearthed in this region, including those of the early, small-walking dinosaurs, have played a crucial role in piecing together the family tree of these creatures. Insight from fossils here informs us about the transition from the dinosaurs' ancestors to the more recognizable giants of the Jurassic. Lastly, we cannot overlook the fossil beds of the Karoo in South Africa, which have shed light on the vertebrate evolution leading up to the age of dinosaurs. Dating back to over 300 million years ago, the area is rich with remains from various prehistoric creatures, helping scientists understand the broader picture of life's history on Earth. These sites, along with others around the globe, collectively enrich our comprehension of dinosaurs, their ecosystems, and the evolutionary journey they undertook millions of years ago. Each discovery not only fascinates us, but also fuels our understanding of the planet's ancient past. Paleontologists rely on a combination of geological, historical, and geographical indicators to identify excavation sites that are likely to yield significant dinosaur finds. One of the primary methods involves studying the geology of an area. Certain rock formations, specifically sedimentary rocks, are known to contain fossilized remains. These formations typically form in environments like riverbeds, floodplains, and shorelines, where conditions were ideal for preserving ancient life. Additionally, paleontologists consult historical records and previous fossil discoveries in the region. If an area has a history of yielding dinosaur fossils, it remains a prime candidate for further excavations. Researchers often map out previous finds to understand the potential spread of dinosaur remains in surrounding areas. In effect, they create a sort of treasure map of locations where ancient reptiles once roamed. Another critical factor in selecting excavation sites is the age of the rocks present. Paleontologists use techniques such as radiometric dating to establish the timeline of geological formations. Knowing the age gives insight into which species may have lived during that period. For example, a site dating back to the late Jurassic might be more promising for certain dinosaur species than one from the earlier Triassic period. Lastly, environmental conditions play a role in site selection. Areas that have not undergone significant geological upheaval, like extensive erosion or tectonic activity, are often more favorable. The preservation of fossils is crucial, so paleontologists seek out locations where they might find well-preserved remains, enhancing their chances of significant discoveries. This careful selection and informed guesswork underpin the ongoing quest to unravel the secrets of these magnificent creatures from our planet's past. To understand the vast timelines of Earth's history and the eras of dinosaurs, scientists turn to the fascinating world of radiometric dating. This technique involves measuring the decay of radioactive isotopes within rocks and fossils. Rocks contain stable and unstable isotopes, and the latter changes over time at a predictable rate, known as its half-life. By determining the ratio of parent isotopes to daughter products within a sample, scientists can calculate how long it has been since the rock formed. One of the most common isotopes used in this process is uranium-238, which decays into lead-206 over the course of about 4.5 billion years. This long half-life makes it particularly useful for dating ancient formations, such as those from the Mesozoic era, which is the age that hosted dinosaurs. Other isotopes with shorter half-lives, such as potassium-40 to argon-40, can be used to date younger rocks and volcanic layers. The ability to date these rocks helps to place a time frame on the fossils found within them, allowing scientists to construct an accurate timeline of the Earth's biological history. An essential aspect of this process is the context in which fossils are found. By examining sedimentary rock layers, also known as strata, scientists can utilize relative dating techniques alongside radiometric methods. Fossils from similar layers can be compared, revealing not only the age of a particular specimen, but also the sequence of events that led to different species' appearances and extinctions. This layering provides a framework that further refines their understanding of when specific dinosaurs roamed the Earth. The synergy between radiometric dating and stratification analysis allows scientists to draw a clear picture of the timeline of dinosaur eras. It is through this meticulous process that we unravel the intricate history of life on our planet. marking the chapters of the Mesozoic era spanning the Triassic, Jurassic, and Cretaceous periods. Each discovery adds another thread to the rich tapestry of evolutionary history, illuminating how dinosaurs lived, adapted, and eventually vanished from the Earth. The breakup of supercontinents like Pangaea and Gondwanaland created dramatic shifts in the Earth's environment, which significantly influenced the evolution and dispersion of dinosaurs. Initially, Pangaea existed about 300 million years ago, bringing together all landmasses into one vast continent. However, during the late Triassic period, around 200 million years ago, it began to split apart. This fragmentation led to the formation of separate landmasses, each with distinct ecosystems. As these supercontinents broke apart, dinosaurs adapted to various climatic conditions and ecological niches. In the northern continent, named Laurasia, dinosaurs evolved in an environment that was markedly different from the southern landmass, Gondwana. This led to diverse adaptations. Some species became large herbivores, able to reach treetops for food, while others evolved into agile carnivores, honing their skills to become efficient hunters. Over millions of years, this adaptability contributed to a rich variety of dinosaur species, varying in size, shape, and lifestyle. Furthermore, geographical barriers emerged as oceans formed and continents drifted further apart. These barriers limited interactions among dinosaur populations, leading to isolated evolution. Dinosaurs on one continent developed different traits and adaptations compared to those on another. For example, while some dinosaurs thrived in the lush environments of what is now South America, others flourished in the drier, desert-like conditions of North America. This isolation contributed to the diversity of species we recognize today. The resulting migration patterns, driven by the availability of resources and climatic changes, also played a crucial role in the dispersion of dinosaurs. As continents shifted and climates fluctuated, some species ventured across land bridges that emerged during periods of lower sea levels. These movements not only allowed for the spread of certain dinosaur species, but also resulted in the mixing of genetic material, further diversifying the dinosaur lineage. Thus, the breakup of supercontinents shaped not just where dinosaurs lived, but how they evolved over millions of years. The evolution of limbs in dinosaurs played a crucial role in their survival and adaptation to changing environments. Throughout their long history on Earth, dinosaurs developed a variety of limb structures that allowed them to navigate, hunt, and escape predators. For instance, the robust forelimbs of theropods, which evolved into birds, provided the ability to grasp and manipulate objects. This adaptation not only enhanced their ability to hunt, but also contributed to the development of flight. Additionally, the structure of the hind limbs was instrumental in the locomotion of different dinosaur species. Some dinosaurs developed long, powerful legs that enabled them to run swiftly, such as the mighty Tyrannosaurus rex, which needed to chase down prey. Others, like the sauropods, had sturdy legs that could support their massive bodies, allowing them to traverse vast distances in search of vegetation. This diversity in limb structure illustrates how different adaptations corresponded to unique survival strategies. The evolution of tails in dinosaurs also provided significant advantages. Tails acted as balancing tools, crucial for maintaining stability while moving at high speeds or maneuvering through their environment. This capability allowed for more agile movements, which were vital when escaping from threats or hunting prey. Moreover, some dinosaurs had tails that helped them communicate or display dominance in social interactions, adding another layer to their survival toolkit. The structural evolution of limbs and tails significantly impacted the survival and adaptation of dinosaurs. By developing specialized limbs for various functions and enhancing mobility and stability with their tails, dinosaurs were equipped to thrive in diverse habitats. The continuous adaptation of their physical features reflects the dynamic relationship between species and their environments, showcasing the remarkable ingenuity of evolutionary processes in shaping life on Earth. The fascinating world of dinosaurs is filled with an array of features, such as crests, frills, and horns. These structures were not just for show, they served vital evolutionary purposes that helped these creatures survive in their respective environments. One of the primary functions of these features was to facilitate communication. Dinosaurs lived in groups or herds, and visual signals would have been crucial for social interaction. For instance, brightly colored crests could help individuals identify each other, communicate their mood, or even attract mates. Moreover, these features often played a significant role in defense mechanisms. In many herbivorous dinosaurs, such as the iconic Triceratops, formidable horns and frills could serve as deterrents against predators. A large frill, combined with sharp horns, could dissuade carnivores looking for an easy meal. These dinosaurs were not just passive victims of their environments. They had evolved various adaptations to protect themselves and their young, ensuring their survival in a world filled with threats. Additionally, crests and frills may have had a role in thermoregulation, allowing certain species to manage their body temperature. The structure of these features could help dissipate heat as they basked in the sun or retain warmth during cooler periods. This adaptability would have provided them with an advantage in diverse climates, from tropical forests to arid landscapes. Lastly, the evolutionary significance of these features can also be tied to mating displays. Sexual selection could drive the development of extravagant traits, as individuals with more pronounced crests or unique frills may have been more attractive to potential mates. This evolutionary pressure would create a dynamic where physical characteristics directly influenced reproductive success, ensuring that those with the most appealing traits passed their genes on to future generations. The colorful array of features in dinosaurs is a glimpse into their complex lives, serving practical purposes in their survival and reproduction. Birds are remarkable creatures, and their lineage can be traced back to a group of dinosaurs known as theropods. These ancient beasts roamed the Earth millions of years ago. The evolutionary journey from dinosaur to bird has resulted in some unique traits that have allowed birds to thrive in a wide variety of habitats. One of the most striking features inherited from their dinosaur ancestors is the lightweight skeletal structure. Birds have evolved hollow bones, which significantly reduce their overall weight without sacrificing strength. This adaptation is crucial for flight, enabling birds to soar through the skies with minimal effort. Additionally, birds possess a fused collarbone, or wishbone, which provides extra stability during flight, a trait that originated in their dinosaur ancestors. Feathers are another standout characteristic that connects birds to theropod dinosaurs. Originally, these structures may have evolved for insulation or display rather than for flight. However, as birds emerged, feathers transformed into the key to aerial propulsion. The development of asymmetrical flight feathers played a pivotal role in their ability to control flight dynamics, allowing for agile movement through the air. Finally, the respiratory system of birds, with its advanced air sacs, is a remarkable evolutionary trait that enhances their ability to sustain flight. This system provides a continuous flow of air, ensuring that birds receive a constant supply of oxygen, which is essential for their high-energy lifestyle. All these traits, lightweight bones, feathers, and a sophisticated respiratory system, paint a vivid picture of how birds are not merely descendants of dinosaurs, but a testament to the incredible adaptability of life on our planet. Evolutionary studies provide a fascinating window into the history of modern birds and their prehistoric ancestors. By examining fossil records, scientists have uncovered a wealth of evidence that traces the lineage of contemporary avian species back millions of years. One of the most significant connections lies in the recognition that birds are, in fact, modern-day descendants of certain theropod dinosaurs. These ancient creatures roamed the Earth during the late Cretaceous period, which was around 100 million years ago. The evidence comes from a variety of sources. Paleontologists have discovered fossilized remains, including feathers, bones, and even nests that exhibit characteristics shared with both dinosaurs and modern birds. One iconic fossil, the Archaeopteryx, often referred to as a missing link, showcases features such as wings and feathers alongside typical reptilian traits. This creature lived around 150 million years ago and serves as a critical piece in understanding the evolutionary transition from dinosaurs to birds. Moreover, comparative anatomy plays an essential role in these evolutionary studies. Researchers analyze the structures of various bird species, noting similarities in bone structure, muscle arrangement, and even the way they feed or make sounds. These comparisons reveal connections that extend beyond mere appearance. Genetic studies further strengthen these findings by examining DNA sequences, allowing scientists to construct evolutionary trees that illustrate how modern birds have diversified and adapted over time. As we continue to unravel the complex web of evolution, it becomes clear that modern birds are not just winged creatures gliding through our skies. They are the living legacy of a lineage that survived extinction and adapted in remarkable ways to thrive in diverse environments. This ongoing journey further emphasizes the interconnectedness of life and the profound story of survival etched into every feathered species that exists today. The design and wear patterns of dinosaur teeth unveil fascinating secrets about their diets and feeding habits. Dinosaurs, like modern animals, exhibited a variety of tooth shapes and structures suited to their specific food preferences. For instance, herbivorous dinosaurs, such as the long-necked Brachiosaurus, sported broad, flat teeth, ideal for grinding tough plant material. This adaptation highlights their feeding style, which involved stripping leaves from trees and breaking down foliage to obtain necessary nutrients. In contrast, carnivorous dinosaurs, like the fierce Tyrannosaurus rex, possessed sharp, serrated teeth designed for ripping flesh. The curvature and sharp edges of these teeth indicate how they hunted and processed their prey. By examining the wear patterns on these teeth, scientists can deduce not only the types of food these creatures consumed, but also the methods they used to consume them. Heavy wear on specific parts of the teeth suggests a consistent diet, confirming that certain dinosaurs specialized in particular food sources. Moreover, when paleontologists study fossilized teeth, they often look for signs of damage or repairs, which can indicate interactions with other animals. For example, teeth that show unusual wear might suggest a struggle with other dinosaurs or the consequences of a predatory encounter. Such intricate details allow researchers to piece together a comprehensive picture of dinosaur life, including their place in the food chain and their ecological roles. By analyzing these dental characteristics, scientists gain invaluable insight into the lifestyles of dinosaurs that roamed the Earth millions of years ago. The teeth act as time capsules, connecting us to ancient ecosystems and allowing us to better understand how these magnificent creatures thrived in their environments. Through these studies, the remarkable story of dinosaur diets continues to unfold, revealing the complexity of life during the age of dinosaurs. The evolutionary development of beaks in certain dinosaurs, particularly the theropods, played a significant role in their survival and diversification. Beaks evolved as adaptations to various diets and environments, providing these creatures with essential tools to access food resources. Instead of teeth, which could be cumbersome for some feeding strategies, beaks allowed for a more efficient and specialized way of foraging. This innovation meant that certain dinosaurs could exploit different ecological niches, leading to greater survival rates and opportunities for speciation. One of the most notable examples of this adaptation is seen in the lineage that eventually gave rise to modern birds. These beaks were initially simple structures that adapted over millions of years. Theropods that developed beaks were able to feed on seeds, fruits, and soft vegetation, which were abundant in their environments. As they evolved, the shape and size of the beak varied widely, reflecting dietary needs. From sharp, pointed beaks for insectivorous diets to broad and flat beaks for those that consumed plant matter. The ability to occupy various niches also drove the diversification of these dinosaurs. With different beak shapes adapted to different feeding strategies, theropods could coexist in the same geographical areas without competing for food. This ecological adaptability was a key factor in their distribution across diverse habitats, from dense forests to open plains. As a result, some species thrived while others faced extinction, leading to a rich tapestry of dinosaur biodiversity. The evolution of beaks in certain dinosaurs is a prime example of nature's ingenuity. It illustrates how a single adaptation can open up a universe of possibilities, influencing survival and playing a crucial role in the diversification that marked the age of dinosaurs. As we look back on this remarkable transition, we gain insights not only into the past, but also into the complex interplay between form, function, and environment that continues to shape life on Earth today.